What if the universe you see, the stars, the space between them, even time itself, isn't quite what it seems? Not in a science fiction way, but in a serious physics lab kind of way. Over the past few decades, physicists and cosmologists have started asking whether reality, as we experience it, might be more like a projection or an emergent pattern than a collection of solid, fundamental things. The deeper we look, the less real the familiar picture of the universe appears to be. Quantum experiments show particles that don't have definite properties until they're measured. The laws of relativity tell us that time can stretch, slow, and even freeze, depending on where you stand. And some of the most elegant mathematical models in modern physics suggest that everything we experience in 3 dimensions could actually be encoded on a distant 2-dimensional surface. It sounds wild, but these aren't fringe ideas anymore. They come from the same physics that underpins our understanding of black holes, cosmic expansion, and the Big Bang. And if they're right, the universe might not be a physical thing in the way we think. It could be information, geometry, or even pure math playing itself out. So how did we end up here, asking if the universe itself is an illusion? Let's start with what that word even means to scientists. When scientists say the universe might be an illusion, they don't mean that it's fake or that nothing really exists. What they mean is that what we experience as reality might not be the ultimate layer of existence. The solid world we interact with every day could be a kind of large-scale effect produced by something much deeper and more abstract. It's not that the world is imaginary, it's that the way it appears might not reflect how it actually works underneath. To understand that idea, it helps to think about what physics has already shown us about perception. You can start with something simple, touching a wall. It feels solid, it resists pressure, and you can't pass your hand through it. But at the atomic level, both your hand and the wall are mostly empty space. The reason you can't go through is that the negatively charged electrons in your skin and those in the wall repel each other. You never actually make contact with the wall. What you feel as touch is an electromagnetic force. The feeling of solidity is real in experience, but it doesn't exist the way it appears to. That's the kind of illusion physicists are talking about, a mismatch between what our senses report and what the underlying physics says is happening. Colour is another example. We treat colour as a property of objects, but it isn't. A leaf looks green not because it contains green, but because it reflects certain wavelengths of light and absorbs others. Your eyes and brain translate those wavelengths into a sensory experience that feels like colour. In that sense, colour exists in perception, not in the physical object itself. Physics keeps showing that our senses deliver a simplified version of a much richer reality. Now take that principle and scale it up to the universe itself. The idea that the cosmos might be an illusion doesn't mean it's a trick. It means that space, time, and matter might not be fundamental things at all. They could be emergent patterns, the way temperature or pressure emerge from countless microscopic particles moving in complex ways. A single atom doesn't have a temperature, but when you have trillions of them interacting, temperature appears as a collective behaviour. In the same way, space and time might only appear once you have enough of whatever the deeper building blocks of reality are interacting in the right way. This is what physicists call emergence. An emergent property isn't a deception. It's a large-scale effect that comes from smaller-scale rules. A brain, for example, is made of neurons that follow electrochemical laws. None of those neurons think on their own, but together they produce something we call consciousness. Reality itself might be doing something similar. Space and time, and everything that happens inside them, could be the emergent result of more primitive elements that don't resemble space or time at all. That's a strange idea because it means everything we take as obvious might be secondary. It also flips one of the deepest assumptions in science, that space and time are the stage on which everything happens. For more than a century, since Einstein's general relativity, physics has treated space-time as a smooth fabric that bends and stretches. But in recent decades, new theoretical work has suggested that even this fabric might be woven from something smaller, networks of quantum information, tiny bits that encode relationships rather than positions. If those relationships change, the geometry of space-time changes with them. To put it simply, the illusion could be the smoothness of space itself. At human scales, it looks continuous, but on the smaller scales, it might be pixelated, quantized. Like the individual pixels that make up an image on a screen, we see a continuous picture only because the pixels are tiny and numerous. Space could be the same way. What we think of as continuous distance might really be the large-scale pattern of an underlying discrete structure. The word illusion also connects to how we define real. In everyday life, something feels real if it behaves consistently, if we can interact with it, and if different people can agree on what they observe. By that definition, the universe is absolutely real. But in fundamental physics, real means something else. It means irreducible, something that can't be explained as the effect of something deeper. And by that standard, the familiar universe might not qualify. It might just be a high-level description of a more basic system made of information, energy, or mathematical relationships that don't look anything like matter. There's a good analogy in computers. When you use a computer, you see icons, folders, and files. You drag and drop things, open programs, and type. But underneath, there are no icons or folders, just electric signals switching on and off inside microchips. The visual interface is there to make the system usable, not to show you what's really going on. Some physicists think our physical reality might work the same way. What we call objects, i.e. forces and particles, could be the interface, not the hardware. They're how the underlying structure of the universe communicates with conscious observers like us. That doesn't mean the universe is a literal simulation. The simulation hypothesis is one possible interpretation, but physicists don't need a programmer or a computer to make this argument. It's enough to recognize that our universe could have layers of description, and the one we live in might not be the base layer. The illusion, then, is our assumption that what we see is the whole picture. There's another reason scientists use the word illusion. Many modern theories describe the universe in purely mathematical terms. Equations can predict everything from the behavior of atoms to the motion of galaxies with incredible accuracy. Some physicists, like Max Tegmark, take this seriously enough to suggest that the universe is mathematics, that what exists fundamentally is a mathematical structure, and what we experience as physical reality is simply how that structure feels from the inside. If that's true, then the material world might be an emergent pattern within mathematics itself. That's an abstract kind of illusion, but it fits the data. The more precisely we measure nature, the more it looks like math all the way down. In this view, the universe doesn't have to be made of anything. It could just be relationships, patterns of information that define how things interact. The illusion is the sense that there are objects sitting in space when, underneath, there might only be the relationships themselves. Reality could be a vast web of connections with no fixed background. The reason this idea has become scientifically respectable is that modern physics keeps running into contradictions whenever we assume the world is straightforwardly real in the classical sense. Quantum mechanics shows that particles don't have definite properties until they're measured. Relativity shows that time doesn't flow the same for everyone, and that space itself bends and stretches depending on energy. Those discoveries force us to give up the idea of a fixed, independent reality sitting out there. Instead, what exists seems to depend on how it's observed, how it's measured, and how it interacts. The deeper we dig, the more reality looks like a flexible, context-dependent process rather than a solid, unchanging thing. So when a scientist says the universe might be an illusion, they're not trying to be poetic or mystical. They're pointing out that physics keeps revealing layers beneath the surface, and that the world we inhabit may be one of those layers, not the foundation. The universe could be a kind of mirage created by information and interaction, a vast emergent phenomenon that looks solid and continuous because our senses and instruments are tuned to that scale. That's why this question matters. It isn't just wordplay. If space and time are emergent, it changes everything about how physics should describe the universe. It means the fundamental laws might not be about particles moving through space, but about how information evolves, how relationships form and dissolve, and how something as concrete as space itself can grow out of something that isn't spatial at all. It's a mind-bending idea, but it's one that modern physics is increasingly willing to take seriously. And it raises an even deeper question. How did humans end up wondering about this in the first place? The suspicion that reality isn't what it seems isn't new. It's ancient. Long before quantum theory or relativity, philosophers were already asking whether the world we see is only a shadow of a deeper truth. The idea that reality might not be what it seems didn't start with quantum mechanics or string theory. Humans have been wrestling with this question for as long as we've been capable of asking questions at all. Every culture that tried to explain existence has, in one form or another, run into the possibility that what we experience isn't the whole story. But in the West, the idea really crystallized in ancient Greece, with Plato's allegory of the cave. Plato imagined a group of people chained inside a dark cave since birth, facing a wall. Behind them a fire burns, and between the fire and the prisoners, others carry objects that cast shadows on the wall. The prisoners can't turn around, they only see the shadows. To them, those moving shapes are reality. If one prisoner escaped and saw the world outside, the real people, trees and sunlight, he would realise that what he thought was the world had only been a projection. Plato's point wasn't about physics, of course. He was talking about perception and truth, that the world we experience through our senses might be just a dim reflection of a more perfect, more fundamental reality. But the metaphor has lasted for over 2,000 years because it captures something timeless. Our intuition that appearances might deceive us, and that the real world might exist on a deeper level. That same tension reappeared in philosophy again and again. Around 400 years ago, René Descartes took it to an extreme. He asked, "How do I know that anything I perceive is real? My senses can fool me, dreams can feel real while they're happening, and thoughts can be manipulated." His conclusion was radical. The only thing he could be absolutely certain of was that he was thinking. Everything else, the external world, even his own body, could be an illusion. That's where "I think, therefore I am" comes from. Descartes wasn't claiming the world is fake. He was saying that our access to reality is filtered through perception, and perception can't always be trusted. Later, Immanuel Kant refined this idea. He argued that the human mind doesn't passively receive reality, it actively shapes it. According to Kant, what we call space and time aren't features of the world out there. They're built-in frameworks our minds use to organise experience. You never encounter the world as it truly is. You encounter it through the lens of your own cognition. Kant called the real, unfiltered world the thing in itself, and he believed it was fundamentally unknowable. We can describe how things appear to us, but we can never step outside our own mental structure to see reality directly. For centuries, those were philosophical ideas. But in the 20th century, physics began to catch up with them, not intentionally, but through experiment. When Einstein developed the theory of relativity, he showed that time and space were not absolute. Two people moving at different speeds could measure time and distance differently, and both could be correct. That discovery shattered the Newtonian idea of a universal clock ticking everywhere in sync. Time turned out to be a relationship between events, not a background that exists independently. That's exactly the kind of thing philosophers had speculated about for centuries, the idea that what we experience as real might depend on how we observe it. Relativity also showed that gravity isn't a force pulling objects together, as Isaac Newton had described it, but the curvature of space and time itself. When you feel your feet pressing on the ground, that sensation isn't gravity pulling you down, it's space-time bending around Earth's mass, guiding your body's natural motion. You're constantly moving through curved space-time, and your weight is your resistance to that curvature. Suddenly, something as concrete as standing on the ground became an illusion of perspective, a side effect of geometry on a cosmic scale. Quantum mechanics, arriving just a few decades later, made the picture even stranger. At the quantum level, particles stopped behaving like tiny marbles following predictable paths. They started behaving like waves of probability, spreading out and existing in many possible states at once until observed. The famous double-slit experiment showed that particles can act as if they know they're being watched, changing their behaviour depending on whether we measure them. It's as if reality doesn't fully exist until it's interacted with or observed, a concept that echoes those old philosophical questions about perception and truth. For the first time, the illusion wasn't just an abstract thought experiment, it was showing up in actual laboratory data. The boundary between what's real and what's observed began to blur. Quantum mechanics made it clear that our everyday intuition, shaped by large-scale experience, doesn't map neatly onto how the universe actually works at small scales. By the mid-20th century, This led to fierce debates among the founders of quantum theory. Niels Bohr argued that it was meaningless to talk about an atom having definite properties before measurement. The act of observation was part of the phenomenon itself. Albert Einstein hated that idea. He famously said, "I like to think the moon is there even if I'm not looking at it." But experiment after experiment began supporting Bohr's side. Reality, it seemed, might not be objective in the way Einstein hoped. What existed depended on how it was measured. That line of thought, reality depending on observation, dovetails almost perfectly with what philosophers like Kant had said centuries earlier. We don't experience the thing in itself. We experience the result of an interaction between the world and our way of perceiving it. In the language of physics, measurement and interaction define what's real. It's striking how similar the logic is. Plato said we only see shadows of a deeper truth. Descartes said we can't trust our senses to show us the world directly. Kant said our perception of time and space is built into our minds, not necessarily part of the universe itself. And then physics, centuries later, started giving us empirical reasons to believe all of that might actually be true, in a measurable, testable way. Once those connections were noticed, the old philosophical question, is the world an illusion, became a scientific one. It no longer belonged just to metaphysics or religion. It became a legitimate topic of research with math, experiments, and data. Physicists began asking, if space and time are not fundamental, what are they made of? If matter doesn't exist until it's measured, what does existence mean at all? From there, the modern conversation took off. Physicists like John Bell, Richard Feynman, and later Stephen Hawking and Leonard Susskind started developing theories that treated reality not as a fixed set of things, but as a network of relationships and information. The more they looked, the more the universe began to look less like a solid machine and more like an elaborate code, a system of patterns and probabilities that only appears stable at our scale. What's fascinating is that this shift didn't happen because anyone wanted it to. Scientists didn't set out to prove that reality is an illusion. They were just following the evidence. Relativity, quantum mechanics, and later cosmology forced them there. Every time we found a deeper layer of description, the solid world got less solid. Time turned out to be flexible. Space turned out to be curved. Particles turned out to be probabilities. Even energy and matter turned out to be interchangeable. By the late 20th century, physics had caught up with philosophy in a way that Plato could never have imagined. The ancient metaphor of shadows on a wall now had mathematical backing. Reality, it seemed, might indeed be a projection of something deeper, a pattern or code from which the visible world emerges. That's where modern ideas like the holographic principle come in. It's a literal physics-based version of Plato's cave. The suggestion that our three-dimensional universe could be a projection of information stored on a distant two-dimensional surface. What began as philosophy has now become one of the most ambitious and technical ideas in theoretical physics. So when we talk about the universe as an illusion, we're not stepping outside science. We're extending a line of questioning that's been running for thousands of years. The difference is that today we have equations and experiments to chase it down. And those experiments keep pointing to the same unsettling conclusion. The world we see may not be the full story. For most of human history, people assumed that the world was straightforward. Objects existed independently, events happened in sequence, and everything had definite properties whether or not anyone was watching. That worldview worked beautifully for everyday life. It was the foundation of Newtonian physics, which could predict the motion of planets, the fall of an apple, and the path of a cannonball with remarkable precision. But in the early 20th century, a new branch of science started revealing cracks in that comfortable picture. Quantum mechanics didn't just add a few new rules to physics, it rewrote the very idea of what reality means. At first, the quantum world didn't make sense to anyone, not even the scientists discovering it. When researchers started studying atoms in detail, they realized that the old mechanical model, tiny particles orbiting like miniature solar systems, simply didn't work. Electrons didn't move in neat circles around nuclei. They jumped, flickered, and existed in strange, uncertain ways. Experiments showed that particles could behave like waves, and waves could behave like particles. Light, which everyone thought was a wave, could hit a metal plate and eject electrons as if it were made of tiny bullets, photons. Meanwhile, electrons, which everyone thought were solid particles, could spread out and interfere like ripples in water. The real shock came when physicists tried to pin down exactly where a particle was. When you look for an electron, you never find it in a fixed spot until you measure it. Before that, it doesn't have a specific position or momentum. It exists as a wave function, a cloud of possibilities. This isn't just a statement about ignorance like saying, we don't know where it is yet. The mathematics of quantum theory suggests that the particle literally doesn't have a definite position until measurement happens. The act of observing seems to create the outcome. One of the simplest experiments that shows this is the double slit experiment. Imagine firing a beam of electrons at a barrier with two narrow openings, or slits, and placing a detector screen behind it. If electrons were tiny balls, you'd expect them to pass through one slit or the other, forming two bright stripes on the screen. But when scientists did the experiment, they saw something else entirely. The electrons formed an interference pattern, a series of alternating bright and dark bands, as if each electron had gone through both slits at once and interfered with itself like a wave. Here's the twist. If you place detectors to see which slit each electron goes through, the interference pattern disappears. The electrons behave like normal particles again, hitting the screen in two distinct stripes. It's as if the simple act of watching changes the behavior of the universe. When unobserved, the electron explores all possibilities. When observed, it decides on one. This experiment has been repeated countless times, with more sophisticated versions using photons, atoms, and even large molecules. The result is always the same. The universe behaves differently, depending on whether information about a system is available. That's a direct challenge to the classical idea that the world exists independently of observation. For Einstein and his generation, this was deeply unsettling. He famously said, "God does not play dice with the universe," arguing that quantum mechanics must be incomplete, that there had to be some hidden variables determining outcomes that we just hadn't discovered yet. Niels Bohr, one of the founders of quantum theory, disagreed. He believed the uncertainty was not a flaw in our knowledge, but a feature of nature itself. "There is no quantum world," Bohr once said. "There is only an abstract quantum physical description." To him, asking what an electron really is before measurement was meaningless. All we can talk about are the results of experiments and the probabilities of different outcomes. This wasn't just philosophical wordplay. Quantum mechanics worked. It explained the behavior of atoms, the stability of matter, the color of light emitted by stars, and the properties of semiconductors. It was the most accurate and successful theory in science. Yet it described a world that made no intuitive sense. According to quantum theory, particles could exist in multiple states simultaneously, a concept called superposition. An electron could be spinning both clockwise and counterclockwise at once, until something forced it to choose. Even entire systems could exist in overlapping realities. The most famous thought experiment illustrating this is Schrödinger's cat. Imagine a cat sealed in a box with a radioactive atom, a detector, and a vial of poison that will break if the atom decays. Quantum physics says that until you open the box, the atom is both decayed and not decayed. That means the cat is both alive and dead in superposition. Only when you look does the system collapse into one outcome. It's a bizarre idea, but it perfectly reflects the math of quantum mechanics. Reality, at its most basic level, seems to be a set of probabilities waiting for an observation to turn them into facts. Over the decades, scientists have developed multiple interpretations to make sense of this. The Copenhagen interpretation, named after Bohr's school of thought, says that quantum objects don't have definite properties until measured. The many worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that all possible outcomes actually happen, just in separate branching universes. In that view, when Schrödinger's cat is both alive and dead, those are two realities that diverge into parallel worlds. Both outcomes are real, but we only experience one. There are other interpretations too. The pilot wave theory, where hidden variables guide particles like invisible currents. Objective collapse models, where quantum states collapse spontaneously without an observer. And relational interpretations, where reality itself is defined only by relationships between systems. None of them have been definitively proven. What's certain is that our classical idea of an objective, observer-independent universe doesn't fit the data. That conclusion got even stronger with experiments inspired by John Bell in the 1960s. Bell derived a mathematical test, now called Bell's theorem, to see whether quantum correlations between particles could be explained by hidden local variables, meaning each particle carried its own internal instructions. Decades of experiments have shown those inequalities being violated, which means quantum mechanics can't be explained by any local, pre-existing reality. Particles separated by vast distances behave as if they share a single, unified state. What happens to one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and for good reason. It appears to defy the speed limit set by relativity. But experiment after experiment has confirmed that the effect is real. It doesn't transmit information faster than light, but it does show that the universe doesn't follow our classical idea of locality. In some deep sense, the universe is more connected than our intuition allows. That discovery, entanglement, may be the most dramatic example of why physicists started thinking in terms of illusion. At the macroscopic level, we experience a world of separate objects with clear boundaries. But at the quantum level, those boundaries dissolve. Two entangled particles can no longer be described as independent entities. They form a single system, even if separated by light years. Our perception of separateness might just be a convenient, large-scale illusion, a simplified picture that breaks down under close inspection. This has profound implications. It means that the properties of things might not belong to the things themselves. Instead, they arise through interactions. An electron's position or spin isn't a built-in feature. It's something that emerges when it interacts with another system, like a measuring device, or ultimately, an observer. The universe may not contain objects in the traditional sense at all. It may contain only relationships, webs of correlations that together create what we experience as reality. Some physicists describe this using the language of information. In quantum mechanics, the universe evolves as a vast network of information exchanges. Measurement is simply one form of information update. This way of thinking leads naturally to the idea that reality might be informational at its core, that what we call matter and energy are ways of organizing and processing information. Space and time could just be the scaffolding that emerges when that information becomes structured in a certain way. What makes this so powerful is that it's not just speculation. Quantum mechanics works with astonishing precision. Its predictions have been tested to 15 decimal places in some experiments, with no known violations. The problem isn't that it's wrong, it's that it describes a world that defies our instincts. The further we follow it, the more our classical assumptions fall apart. At the everyday level, things still seem solid and deterministic because quantum effects average out. A rock doesn't exist in a superposition of places because its atoms are constantly interacting with the environment. That interaction, called decoherence, forces quantum systems to choose a classical outcome, effectively creating the illusion of stability. In other words, the classical world we experience might be what quantum uncertainty looks like when you zoom out far enough. That's why scientists call it an illusion. It's not that reality doesn't exist, it's that the smooth, predictable world we live in is a kind of large-scale mirage created by countless tiny, probabilistic events. Beneath every stable atom, every solid object, every moment of time, there's a sea of uncertainty and entanglement. The universe looks classical only because we're looking from too far away to see the quantum chaos underneath. And as strange as all this sounds, it might not even be the strangest part. Because when you take quantum mechanics and combine it with what we know about space-time, gravity, and black holes, you get something even more radical, the possibility that our entire universe, the space we move through, the matter we're made of, even time itself, could be a holographic projection of information encoded elsewhere. When quantum mechanics first suggested that particles could influence each other instantaneously across vast distances, even Einstein found it absurd. He dismissed the idea as spooky action at a distance. To him, no effect could travel faster than light, and nothing should depend on a measurement performed somewhere else. That principle, called locality, was one of the cornerstones of physics. Locality meant that objects were only affected by their immediate surroundings, not by distant events happening light years away. But quantum mechanics refused to play by that rule. The story of how that rule broke begins with entanglement. Entanglement is one of the most counterintuitive phenomena in science. When two particles become entangled, they share a quantum state. You can measure one and instantly know the state of the other, no matter how far apart they are. For example, if two electrons are created together in such a way that their spins must add up to 0, then measuring one as up instantly tells you the other must be down. That might sound like common sense. Maybe each electron already had its spin decided before you measured them, but that's the point. According to quantum theory, they didn't. The spins weren't predetermined. They existed in superposition until the measurement forced them to take definite values. And yet, once measured, their results always matched perfectly. For years, Einstein, along with Boris Podolsky and Nathan Rosen, argued that this must mean quantum mechanics was incomplete. Their 1935 paper, often called the EPR paradox, suggested there must be hidden variables, undiscovered properties that carried information about the outcome ahead of time. Otherwise, it seemed like one particle was somehow communicating with the other faster than light. Einstein's instincts told him that reality had to be local and objective. Particles should have real properties that exist whether we look or not. But in 1964, a Northern Irish physicist named John Bell came up with a way to test that assumption directly. He derived what's now called Bell's theorem, which says that if the universe obeys both locality and realism, meaning that physical properties exist independently of observation, then certain mathematical inequalities must hold in experiments with entangled particles. If those inequalities were ever violated, it would mean the universe doesn't work that way. At first, it was an abstract argument, but within a decade, physicists started testing it in the lab. In 1972, the first major experiment by Stuart Friedman and John Clauser used entangled photons and found results that matched quantum mechanics and violated Bell's inequalities. Later, more precise tests in the 1980s by Alain Aspect in France closed several loopholes and showed even stronger violations. Over the following decades, experiments became ever more refined, using entangled light, electrons, and even atoms. In 2022, Aspect, Clauser, and Anton Zeilinger won the Nobel Prize for this work. The conclusion was unavoidable. The world does not obey local realism. That phrase, no local reality, is as unsettling as it sounds. It means that the universe cannot be both local, nothing faster than light, and real. Objects having definite properties independent of measurement. One of those has to give. And since experiments confirm that nothing actually travels faster than light, the part we're forced to give up is local realism itself. The properties of things do not exist independently of the whole system. In a very literal sense, the universe is fundamentally interconnected. It's hard to overstate how strange this is. Imagine two photons created together in a lab, then sent in opposite directions, one to New York, the other to Tokyo. If a scientist in New York measures her photon's polarization, she instantly knows what the results in Tokyo will be, even if there hasn't been time for light to travel between them. It doesn't mean information has traveled faster than light, but it does mean the two results are linked in a way that no classical explanation can reproduce. There's no signal being sent. It's as if both measurements are part of one unified event that spans both locations. This defies the picture of the universe as a collection of separate things. In quantum mechanics, separateness may be an illusion. The deeper truth might be that everything is part of one giant non-local system. What we see as distinct objects and events are just parts of that web, appearing temporarily independent. This isn't a philosophical statement. It's what the math and experiments tell us. Some physicists describe this as quantum holism. In classical physics, you can describe the whole by adding up its parts. In quantum physics, the whole has properties that none of the parts possess individually. You can't predict the outcome of an entangled system just by describing its components separately. The information that defines the system exists only in their combined state. That's why measuring one instantly affects the other, not because something travels between them, but because the two are really one. If this sounds abstract, consider that it's not just a curiosity. It's a measurable, exploitable phenomenon. Quantum entanglement is now used in quantum communication, quantum computing, and cryptography. In quantum teleportation, for example, the state of a particle can be transmitted from one place to another without physically moving the particle itself, using entanglement as the bridge. These technologies work precisely because the universe really does behave in this deeply connected, non-local way. So what does this have to do with the idea that the universe might be an illusion? Non-locality undermines one of our most basic intuitions, that there are independent objects with intrinsic properties. If quantum systems can't be separated, then what we call things are not fundamental entities at all. They're temporary patterns of correlation within a single, interconnected whole. The boundaries we see between objects might be artifacts of how our senses and instruments divide up reality, not features of reality itself. This line of reasoning has led some physicists to suspect that space itself, the very concept of distance, might not be fundamental either. If two particles can be entangled across vast separations, maybe those separations aren't as real as they seem. In fact, several theories now propose that space could emerge from entanglement, that the geometric structure of the universe might literally be built out of quantum relationships. In that picture, the smooth fabric of spacetime described by Einstein is like a large-scale illusion created by countless entanglement links woven together. This is where the holographic principle starts to come into the story. The principle was first developed to solve paradoxes about black holes, but its implications stretch far beyond that. It suggests that the entire universe might be describable as a kind of information network, a system where what happens in 3 dimensions could be encoded on a 2-dimensional surface. Non-locality, rather than being a weird exception, could be the rule that makes that possible. To see how this works, it helps to think about what physicists discovered when they studied black holes in the 1970s. According to classical physics, anything that falls into a black hole is gone forever. But quantum mechanics says that information can't be destroyed. That contradiction led to the famous black hole information paradox. The solution came from the realization that the information about everything that falls in might actually be stored on the surface of the black hole, not inside it. The area of the event horizon, the boundary around the black hole, turns out to measure the amount of information it contains. That discovery, made by Jacob Bekenstein and Stephen Hawking, led to a shocking idea. Maybe the information describing the contents of a volume of space is always stored on its boundary. That's the holographic principle in a nutshell, the notion that the entire 3-dimensional universe could be like a hologram, with everything we experience as 3D encoded on a distant 2-dimensional surface. And non-locality is what makes it possible. Entanglement links everything together across space, blurring the very concept of distance, so that the universe doesn't need to be locally real in the way we imagine. In that sense, when scientists talk about the universe as an illusion, they don't mean it's imaginary or simulated. They mean that our everyday picture of separate local objects interacting in space might be the wrong framework entirely. Reality could be a web of correlations, where what happens in one place depends on relationships that transcend space itself. Einstein's spooky action at a distance turned out not to be a flaw in quantum mechanics, but a clue that reality is more deeply unified than anyone expected. The universe might not be made of things, it might be made of information. And that idea, strange as it sounds, is the foundation for one of the most mind-bending hypotheses in all of physics, that everything we see around us could be a projection from a deeper, information-rich surface beyond the limits of space and time. When people hear that the universe might be a hologram, it sounds like science fiction, as if we're living inside a cosmic projection. But the holographic principle isn't about fantasy. It's one of the most serious, mathematically grounded ideas to come out of theoretical physics in the last 50 years. It started as a way to solve a paradox about black holes, but its logic turned out to be so powerful that it might describe the entire universe. If true, it would mean that everything we see in 3 dimensions, every planet, atom, and patch of empty space, could actually be the projection of information stored on a 2-dimensional boundary far away. The story begins in the 1970s when physicists were trying to understand what happens to matter that falls into a black hole. According to Einstein's general relativity, a black hole is a region where gravity is so strong that nothing, not even light, can escape. Whatever crosses its boundary, the event horizon, is gone forever. But in the 1970s, Jacob Bekenstein and Stephen Hawking discovered something unexpected. They realized that black holes aren't completely black. Hawking showed that quantum effects near the event horizon allow black holes to emit faint radiation, now called Hawking radiation. And if they emit radiation, that means they can eventually evaporate. That's where the problem appeared. If a black hole can disappear, what happens to the information about what fell in? In ordinary quantum mechanics, information can never be destroyed. Every process is reversible in principle. If you know the starting conditions perfectly, you can always work backward. But if a black hole swallows information and then vanishes, that rule breaks. The universe would lose track of what once existed. Hawking himself initially believed that information really was lost, that black holes destroyed it completely. But that conclusion horrified many physicists because it violated the basic principles of quantum theory. Bekenstein made an important observation that changed everything. The amount of information a black hole can contain isn't proportional to its volume, but to its surface area. The more surface area the black hole has, the more information it can hold. That was shocking because we normally think that the capacity of an object, say a box, depends on its volume. A bigger box holds more stuff. But black holes seem to break that rule. Their storage capacity scaled with the area of their boundary. It was as if the information describing everything inside was somehow written on the surface. That realization planted a seed. Maybe the same principle applies to the entire universe. Maybe the total amount of information needed to describe a region of space doesn't depend on how big it is, but on the area of its boundary. In the 1990s, theoretical physicist Gerard T. Hooft proposed that this might be a general property of nature, that the world we experience in 3 dimensions could be a kind of holographic projection from a 2-dimensional surface. Leonard Susskind later developed this idea into what's now called the holographic principle. The word hologram here isn't just poetic. In a real hologram, like the ones used on credit cards or security seals, a 2-dimensional surface encodes information that appears as a 3-dimensional image when illuminated. Every part of the surface contains the full image, just at lower resolution. The holographic principle takes that metaphor literally. It says the 3D world we see could be an image generated by information encoded on a cosmic surface. The mathematics that gave this idea real traction came in 1997 from Juan Maldacena, an Argentine physicist working on string theory. He proposed a relationship called the ADS/CFT correspondence, short for anti-de Sitter/conformal field theory. It's one of the most celebrated discoveries in modern theoretical physics. Maldacena showed that a type of universe with gravity, described by string theory in an anti-de Sitter space, could be exactly equivalent to a universe without gravity that exists on its lower dimensional boundary. Everything happening in the 3D world, including gravity, matter, and the curvature of space, could be described completely by a 2D quantum field theory on the edge. 2 very different descriptions of reality turned out to be mathematically identical. In practice, our universe isn't an anti-de Sitter space. It's expanding, and it doesn't have that specific geometry. But Maldacena's correspondence provided a proof of concept. It showed that the holographic principle isn't just a metaphor, it's a real physical possibility. It's consistent, calculable, and deeply elegant. For many physicists, it offered the first solid clue about how quantum mechanics and gravity, 2 pillars of physics that have stubbornly resisted unification, might fit together. The implications are enormous. If the holographic principle applies broadly, then the space we move through, the particles that make up matter, and even the flow of time might all be emergent phenomena, not fundamental ingredients of reality, but large-scale effects of information encoded elsewhere. What we call inside the universe could be a kind of projection from the outside. You can think of it this way. Imagine standing inside a giant cosmic sphere. The interior looks like a vast 3-dimensional space filled with stars and galaxies. But everything happening inside could be fully described by data imprinted on the surface of the sphere. The depth you experience, the distances between objects, the flow of time, the volume of space, might be real to you, but they could all arise from the way that information is arranged and processed on that boundary. That's an almost impossible idea to visualize, but physicists can test its logic mathematically. When they apply holographic principles to black holes, for instance, they can reproduce Hawking's results perfectly. The surface of the black hole, its event horizon, behaves like a 2-dimensional information screen that encodes everything happening inside, that not only preserves information, but also maintains the consistency of quantum mechanics. No information is lost, it's just scrambled across the surface in an unimaginably complex way. Some researchers have even looked for hints of holographic structure in our own universe. In 2017, a team analysing data from the Planck satellite, which maps the cosmic microwave background, reported subtle statistical patterns that could be consistent with a holographic universe model. The results were tentative and controversial, but they suggested that if the universe is holographic, traces of that might be imprinted in the afterglow of the Big Bang itself. Other studies are exploring whether the strange correlations in quantum entanglement could be signatures of an underlying holographic structure. The deeper appeal of the holographic principle is that it might explain why the universe feels both richly complex and strangely efficient. If everything we experience is encoded on a simpler boundary, then reality itself could be fundamentally informational, like a vast data structure unfolding in ways that produce the appearance of physical laws. That doesn't make it less real. It just means that real might mean something different than we think. What's especially elegant about this idea is that it ties together so many puzzles. It helps explain black hole entropy, unifies gravity with quantum theory, and suggests a mechanism for how space and time could emerge from something more fundamental. In some theoretical models, space literally is built from entanglement, from the connections between bits of quantum information. As those connections increase, the geometry of space grows. When they decrease, space itself can shrink or even tear. In that sense, the universe isn't a static backdrop, but a living network of relationships, constantly generating the illusion of space through interaction. That brings us back to the question of illusion. When physicists talk about a holographic universe, they don't mean that it's fake or that we're trapped in a digital simulation. They mean that our experience of three-dimensional reality might be the way a two-dimensional information structure looks from the inside. What we call space could be the emergent geometry of information, and what we call matter could be patterns within that geometry. It's real, but not in the straightforward material sense we once assumed. For many scientists, this idea represents a profound shift in perspective. It replaces the notion of a universe made of stuff with a universe made of information, relationships, and mathematics. It suggests that everything we see, from atoms to galaxies, could be the visible side of a deeper informational fabric that we're only beginning to understand. And that raises an even more surprising question. If the universe we see is a projection, what happens when we look at its motion through time? Could the expansion of the cosmos itself be another kind of illusion, a side effect of how we're reading the underlying information? Some recent theories are beginning to suggest exactly that. For nearly a century, the expansion of the universe has been one of the most accepted facts in cosmology. Since Edwin Hubble first observed in the 1920s that distant galaxies were moving away from us, scientists have pictured space itself stretching like an inflating balloon. The farther a galaxy is, the faster it recedes. That discovery was revolutionary. It showed that the universe had a beginning, the Big Bang, and that it's been growing ever since. But a growing number of physicists now wonder if we've been interpreting that evidence the wrong way. What if the expansion of the universe isn't what it seems? What if it's another layer of illusion? It's a bold claim, and it doesn't come from fringe thinkers. Some recent theoretical work suggests that what we interpret as cosmic expansion could be a side effect of changes happening not to space, but to the properties of matter itself. In 2024 and 2025, several studies propose that the redshift we see, the stretching of light from distant galaxies, might not necessarily mean that galaxies are flying apart. Instead, it might mean that the scale of fundamental particles, or even the constants of nature, has been changing over time. In other words, the ruler we use to measure the universe might itself be slowly changing. The key observation behind the idea is that we never directly see space stretching. What we measure is light. When we look at distant galaxies, their light is shifted toward the red end of the spectrum. The longer the light travels, the more it stretches. The standard interpretation is that this stretching happens because space itself is expanding. The wavelengths of light are literally being stretched as the fabric of the universe grows. But there's another way to look at it. Maybe the light isn't stretching. Maybe the things we use to measure it are shrinking. In physics, there's a concept called conformal symmetry, which means that the laws of nature can look the same, even if all lengths and times are scaled up or down together. Some recent cosmological models take this idea seriously and propose that instead of space expanding, particle masses are slowly increasing. If the size of atoms or the energy of photons changes in a coordinated way, then light from the past would naturally appear redshifted, even in a static universe. What we interpret as the expansion of space could be a kind of optical illusion created by shifting physical standards. This might sound speculative, but it's rooted in a real motivation to explain why the universe's expansion seems to be accelerating. In the late 1990s, astronomers discovered that distant supernovae were dimmer than expected, leading to the conclusion that cosmic expansion was speeding up. To explain it, scientists introduced dark energy, a mysterious force making space expand faster and faster. Dark energy has never been observed directly, yet it's now thought to make up about 70% of the universe. It's an elegant solution, but also a troubling one. If dark energy doesn't exist, then we've misunderstood something fundamental about how we interpret cosmic light. Some physicists, like Lucas Lombrazer at the University of Geneva, have proposed that the acceleration might not be real at all. In his models, published in 2023 and refined in 2025, the universe doesn't expand in the way we think. Instead, the masses of particles slowly increase over time. That means the yardstick of physics, the scales we use to measure distances and times, changes, creating the illusion of acceleration. The universe could be static on large scales, while everything inside it gradually evolves in a synchronized way. From our perspective, it would look exactly like expansion, even though space itself isn't stretching. This interpretation solves several long-standing problems at once. It removes the need for dark energy, which has always been an awkward placeholder in our equations. It also sidesteps the Hubble tension, the mismatch between measurements of the universe's expansion rate from nearby galaxies and from the early universe's background radiation. If expansion isn't fundamental, then the conflict between those measurements might not be a conflict at all, just a misreading of evolving physical constants. There's another layer to this argument that fits beautifully with the holographic idea discussed earlier. If the universe is fundamentally informational, then what we perceive as expansion could be a change in how that information is encoded. The number of bits describing the universe might stay constant, but their configuration could evolve, giving the illusion of growth. It would be like watching a movie where the resolution increases over time. The screen doesn't get bigger, but the details become richer, creating the sense of expansion. From this perspective, the Big Bang might not have been an explosion of matter into space, but a phase transition, a reorganization of information. The early universe could have existed in a dense, low information state that gradually unfolded into the richly structured cosmos we see today. Expansion would then be an emergent effect of information rearranging itself, not a literal stretching of space. There's historical precedent for this kind of rethinking. Before Einstein, people thought gravity was a force that pulled objects together. Einstein showed that what we called a force was actually the curvature of space-time. The appearance of attraction was an illusion caused by geometry. In the same way, what we now call expansion might be a large-scale illusion caused by changes in the underlying informational or physical structure of the universe. Critics point out that these alternative models are speculative, and that the standard picture of expansion, based on general relativity and supported by multiple observations, still fits the data extremely well. The cosmic microwave background, the distribution of galaxies, and the abundance of light elements all match what we'd expect from an expanding universe. But even within that framework, physicists acknowledge that what we call expansion is subtle. Galaxies aren't really flying apart through space. The space between them is stretching. But locally, within galaxy clusters or solar systems, gravity keeps everything bound. The expansion isn't a motion through space. It's a change in the geometry of space itself. That distinction sounds technical, but it highlights how abstract the idea already is. We can't observe the stretching of space directly. We infer it from light. That means our entire picture of the universe's growth depends on interpretation, and interpretations can change. If new evidence shows that fundamental constants or particle masses evolve over time, the entire story of cosmic expansion might have to be rewritten. There's also an emotional dimension to this question. The expanding universe has been part of our collective imagination for nearly a century. It gives us a sense of direction, a universe that grows, cools, and evolves from simplicity to complexity. To suggest that this grand unfolding might be a perceptual effect feels unsettling. But that's what good science does. It challenges the stories we tell about the world when the evidence points somewhere deeper. If expansion really is an illusion, then the universe could be far more stable and self-contained than we thought. Instead of racing toward an eventual heat death, it might exist in a steady equilibrium, constantly recycling information in new forms. What we experience as change and growth could be the visible face of an underlying balance, a cosmic mirage created by our limited point of view. And even if the standard model holds, the holographic and informational perspectives remind us that our usual way of picturing expansion, galaxies moving through space, isn't the whole truth. What's really expanding might not be space itself, but our description of it, our relationship to it, or the information that defines it. Either way, the pattern keeps repeating. The more deeply we study the universe, the less it behaves like a simple physical thing, and the more it behaves like an abstract system of information and relationships. Expansion might be one of those relationships, a change in how we experience the code, not the code itself. And that leads to the next big mystery. If expansion might be an illusion, could the other great unknown in cosmology, dark energy, also be an illusion? Some scientists think it might be, and their reasoning takes the illusion idea to an even deeper level. When we look at the universe through telescopes and detectors, almost everything we see, stars, planets, galaxies, gas, dust, adds up to less than 5% of what's actually out there. The other 95% is invisible. About 27% is thought to be dark matter, and roughly 68% is dark energy. Together they dominate the cosmos, shaping its structure and fate. And yet, despite decades of searching, no one has ever directly detected either one. That's led some scientists to a radical question. What if dark matter and dark energy don't actually exist? What if they're illusions created by how we interpret gravity, space, and time? Let's start with dark matter. In the 1930s, Swiss astronomer Fritz Zwicky noticed something odd when studying galaxies in the Coma cluster. The galaxies were moving much faster than their visible mass could account for. If gravity was working the way Newton and Einstein described, the cluster should have flown apart long ago. Zwicky proposed that there must be some invisible mass, dunkler materia, or dark matter, holding everything together. For decades, that idea gained strength. In the 1970s, Vera Rubin's observations of spiral galaxies showed that stars at the edges orbited just as fast as those near the centre, when gravity predicted they should move more slowly. The simplest explanation was that a massive halo of unseen matter surrounded each galaxy. Since then, every line of evidence, galaxy rotation curves, gravitational lensing, the cosmic microwave background, has pointed to something exerting extra gravity that we can't see. The catch is, no one knows what it is. Physicists have proposed all kinds of candidates: weakly interacting massive particles, WIMPs, axions, sterile neutrinos, primordial black holes. Huge detectors buried deep underground and in space have been built to find them. So far, every search has come up empty. That's where the illusion hypothesis enters. Some physicists argue that dark matter might not be a thing at all, but a sign that we're misreading how gravity works on large scales. One of the best-known alternatives is called MOND, for Modified Newtonian Dynamics, proposed by Mordechai Milgram in the 1980s. He suggested that at very low accelerations, like those experienced by stars at the outskirts of galaxies, gravity doesn't behave exactly as Newton predicted. Instead, it weakens more slowly. This tweak reproduces galaxy rotation curves almost perfectly without any dark matter. MOND has its issues. It struggles to explain galaxy clusters and the cosmic microwave background. But it started a movement. Variants like TVES, tensor vector scalar gravity, and emergent gravity, proposed by Eric Verlinde, take the idea further. Verlinde's model, introduced in 2016, treats gravity not as a fundamental force, but as an entropic effect, something that emerges from the statistical behaviour of microscopic information. In that framework, what we call dark matter is a kind of residual effect of the way information and entropy are distributed through space. It's not a hidden substance, but a shadow of deeper physics. That's an elegant idea because it ties directly into the holographic and informational view of the universe. If gravity itself is emergent, then its apparent anomalies could easily be illusions. In Verlinder's equations, galaxies rotate the way they do not because of an invisible halo of matter, but because gravity remembers the distribution of information in the surrounding space. In other words, dark matter might not exist, but the illusion of it would still behave exactly as if it did. Now consider dark energy, the other great unknown. It's the name we give to the observed acceleration of the universe's expansion. A discovery made in 1998 using distant supernovae as cosmic yardsticks. When astronomers measured how fast galaxies were moving away, they found that the rate was increasing, as if some invisible pressure were pushing space apart. The simplest explanation was a cosmological constant, an energy inherent to the vacuum of space itself. Einstein had proposed such a constant decades earlier, then abandoned it, calling it his biggest blunder. Ironically, it came back to life as the leading explanation for cosmic acceleration. The problem is, no one knows what this dark energy actually is. If it's vacuum energy, the energy of empty space predicted by quantum field theory, the numbers don't match. The theoretical value is about 120 orders of magnitude larger than what we observe. That's the biggest discrepancy between theory and observation in all of science. To fix it, cosmologists simply adjust the constant to fit the data. It works mathematically, but it feels unsatisfying, like a patch, not a real explanation. This has led to a growing sense that dark energy might be a mirage. Some cosmologists suggest that the apparent acceleration could arise from the way we average cosmic structures. The universe isn't perfectly smooth, it's lumpy, filled with galaxies, clusters, and voids. If you model that lumpiness accurately, the observed acceleration can emerge naturally, without any new force. This idea is sometimes called timescape cosmology or back reaction theory. In that picture, the expansion we see might just be an illusion caused by our vantage point inside a clumpy universe. Another possibility, explored by researchers like Niayesh Afshordi, is that dark energy might not be a separate substance, but a side effect of quantum fluctuations at cosmic boundaries. Essentially, the universe's geometry resonating like a membrane. That connects directly to holographic principles. If the universe's information is stored on a boundary, then what we interpret as dark energy could be the way that information density changes over time. The universe would appear to expand faster, not because space is stretching, but because the informational surface encoding it is changing. Even in mainstream cosmology, there's growing recognition that dark energy might not be fundamental. It could be a placeholder for deeper processes we don't yet understand. Some physicists, including those working on variable fundamental constants, suggest that what looks like acceleration might result from changing particle masses or energy scales, similar to the idea discussed in the previous section. In that view, the push of dark energy could be an illusion caused by evolving standards, a side effect of cosmic bookkeeping. These ideas are provocative, but they share a pattern. The more we look at the universe, the more its mysteries resemble artifacts of how we measure and interpret it. Dark matter might be the illusion of missing gravity. Dark energy might be the illusion of changing scales. Both could emerge naturally from a deeper, informational structure that we haven't yet described in the language of traditional physics. If that sounds radical, it's worth remembering that physics has gone through paradigm shifts like this before. The concept of heat used to be explained as a mysterious fluid called caloric. Electricity was thought to be two invisible substances called vitreous and resinous fluids. Those ideas worked until scientists realized that heat was just molecular motion and electricity was the flow of charge. What we call dark energy and dark matter might turn out to be the same kind of transitional concepts, useful illusions pointing toward a truer, deeper framework. What makes this shift especially compelling today is that it lines up with everything else modern physics is discovering. Quantum entanglement tells us that reality is non-local. The holographic principle tells us that information might be more fundamental than space. And theories like emergent gravity tell us that what we think of as forces could be the side effects of information organizing itself. If those are all true, then the invisible stuff we've been chasing might not exist at all. Not because it's imaginary, but because we've been looking at the shadows instead of the source. That realization brings us to one of the boldest ideas in all of modern science, that maybe the universe isn't physical in the traditional sense at all, that it might be, at its core, a mathematical structure where the distinction between real and illusion is simply a matter of perspective. For most of us, time feels like the most obvious feature of existence. We wake up, we age, we remember the past but not the future. Everything we know, movement, change, cause and effect, seems to depend on time flowing forward. But physics keeps telling a different story. At its deepest levels, the universe doesn't seem to care about before and after. The equations that describe reality work just as well backward as forward. Time, as we experience it, might not be a fundamental feature of the cosmos at all. It might be another kind of illusion. Einstein was the first to make that claim explicit. When he developed general relativity in 1915, he showed that time and space aren't separate things. They form a single four-dimensional structure called space-time, where what we think of as past and present and future all coexist. Events that we experience in sequence are just different points in that structure. To a being who could see the universe from outside space-time, there would be no flow, just a vast frozen landscape where everything that ever happened or ever will happen already exists. Einstein called this the block universe. In a letter written after the death of a friend, he put it simply: the distinction between past, present, and future is only a stubbornly persistent illusion. In the block universe, nothing actually happens. The Big Bang, the formation of the Milky Way, your birth, and the far future of the cosmos are all part of one unchanging whole. The feeling that time flows from moment to moment is not a property of reality itself. It's a feature of how conscious beings experience that reality. We live inside the block and perceive it slice by slice, the way a flatlander moving through a 3D sculpture would experience each cross-section as a separate moment. This view might sound static, but it fits perfectly with what physics shows us. The equations of general relativity don't include a preferred now. There's no cosmic clock ticking everywhere at once. Time is relative. It moves differently for different observers, depending on their speed and the curvature of space-time around them. A person orbiting near a black hole experiences time far more slowly than someone far away. To one observer, two events might happen simultaneously. To another, one comes before the other. There's no universal present moment to anchor them. If time isn't flowing, why do we experience it as if it does? One answer lies in entropy, the measure of disorder in a system. In thermodynamics, entropy tends to increase, and that increase gives direction to what we call the arrow of time. You can scramble an egg, but you can't unscramble it. You can burn paper, but not unburn it. That asymmetry doesn't come from the laws of physics. Those are time-symmetric. But from the initial conditions of the universe. The Big Bang began in an extremely low entropy state, and everything since has been a gradual rise toward higher entropy. Our brains, memories, and sense of causation are all products of that process. We remember the past because entropy increases toward the future, not the other way around. In other words, the flow of time might be an emergent illusion created by entropy's direction, not a fundamental feature of the universe. The movie of reality isn't actually playing. It's all there, start to finish. But we experience it one frame at a time because of how physical processes, including our consciousness, move through it. Quantum mechanics adds another layer of strangeness. In the quantum world, many equations, including Schrödinger's equation, don't include time as a fundamental variable. They describe systems evolving in a kind of abstract mathematical space. Time appears only when certain approximations are made, or when systems interact in specific ways. Some physicists, like Carlo Rovelli, have built entire theories of timeless physics around this idea. In his framework of loop quantum gravity, space and time both emerge from networks of relationships among quantum events. There is no ticking cosmic clock, only interactions. What we perceive as time passing is the pattern of those interactions unfolding. This has led to one of the most striking ideas in modern physics, that time is not something the universe has, it's something the universe does. It's a measure of change, not a container in which change happens. If nothing changes, time stops. But change itself may not require an underlying timeline. It could just be the comparison between different states of the same system. That's why some physicists prefer to say that time is a measure of correlation. When things evolve together, we define one process as the clock and another as the event, but both are part of the same relational structure. There's also a radical interpretation called the timeless universe or emergent time hypothesis, which proposes that time is a property that only appears when we have enough complexity. The way temperature appears only when enough particles interact. In a small, simple quantum system, there's no meaningful sense of before and after. Time only emerges at macroscopic scales when information and entropy give rise to history. That means that in the deepest layers of physics, below space-time, below quantum fields, there may be no time at all, just relationships that, when viewed from our perspective, look like temporal evolution. If that's true, then the flow of time, the thing that feels most undeniable to us, is a projection of our minds interpreting those relationships. Consciousness stitches events together in sequence because that's how our brains process information. We evolve to experience cause and effect because it helps us survive. But to the universe, all causes and all effects exist simultaneously. This view has profound implications. It challenges not just physics, but philosophy and even personal identity. If the block universe is real, then every version of you that ever existed, every age, every decision, every possible future, already exists within the fabric of space-time. You don't move through time, you are a four-dimensional structure extended through time. The you reading this sentence is one slice of that structure, just as real as the you who first learned to read, or the you who will someday remember reading this. That might sound unsettling, but it can also be strangely comforting. If time is an illusion, then nothing is ever truly lost. Every moment, every thought, every event exists forever as part of the cosmic tapestry. Change is just the way our consciousness scans that tapestry, frame by frame. In physics, this perspective is gaining renewed attention, not as a philosophical curiosity, but as a potential clue to unifying quantum mechanics and relativity. In quantum gravity research, the concept of a timeless universe is not just poetic, it's practical. When physicists try to merge Einstein's equations with quantum theory, time often disappears from the mathematics entirely. It doesn't fit at the fundamental level, suggesting it's not fundamental at all. Instead, time may be something that appears when certain conditions, complexity, interaction, memory, come together. And this leads to a deeper question. If time and space are both emergent illusions, what role does the observer play? Because if the universe is timeless at its core, yet we experience it moment by moment, something about consciousness itself might be helping to create the illusion of flow. Maybe time exists not out there, but in the act of observation, in the way information becomes ordered through awareness. That question takes us to the next frontier, the strange link between observers and reality itself. For centuries, science and philosophy kept consciousness and physics in separate boxes. Physics dealt with matter, energy, and the laws that govern them. Consciousness was left to psychology and philosophy. But the deeper we've gone into quantum mechanics, the harder it's become to keep those boxes apart. The observer isn't just a passive witness in the quantum world. Observation seems to do something. It turns possibilities into realities. That idea unsettled even the founders of quantum theory, because it implies that consciousness might play an active role in shaping what we call the real world. The tension began with the quantum measurement problem, the puzzle of how and when a quantum system chooses a definite state. Before measurement, a particle exists as a wave function, a mathematical cloud of probabilities describing all possible outcomes. The act of measurement collapses that wave function into a single result. But what exactly counts as a measurement? Is it just a detector clicking in a lab? Is it the moment a human sees the result? Or is it something deeper, a fundamental link between observation and existence itself? In the early days of quantum theory, physicists like Niels Bohr and Werner Heisenberg argued that reality only becomes definite when observed. Bohr's Copenhagen interpretation said that it's meaningless to talk about an electron's position before measurement. The concept of position itself only makes sense when you measure it. This interpretation doesn't necessarily require consciousness. but it does make the act of observation central to reality's behaviour. Then came thinkers like John von Neumann and Eugene Wigner, who went further. Von Neumann showed that you can mathematically push the measurement problem as far as you want, from the particle to the detector, to the measuring device, to the neurons in the scientist's brain. But at some point, something non-physical must collapse the wave function. Wigner suggested that consciousness might be that final step. When awareness enters the chain, probability becomes fact. That idea, often called the observer effect, has been misunderstood and misused in popular culture, but in physics it has a specific meaning. It doesn't say that you can manifest reality just by thinking about it, or that consciousness creates the universe out of nothing. It says that the act of observation, in the broad sense of information becoming definite, is built into the structure of quantum mechanics. The universe doesn't seem to evolve as a fixed objective system, independent of observation. Instead, what we call reality emerges through interactions that include observers as participants. This has led some physicists to propose what's called the participatory universe idea, inspired by John Archibald Wheeler. Wheeler, one of the great theoretical physicists of the 20th century, helped coin the term black hole, but later in life he turned his attention to the nature of reality itself. He asked a deceptively simple question: does the universe exist if there's no one to observe it? His answer was equally simple: no meaning without measurement. Wheeler imagined a cosmos in which observation and existence are intertwined, where the universe doesn't come pre-packaged with definite properties, but crystallizes into reality through acts of measurement. To illustrate this, he proposed a thought experiment called the delayed choice experiment. Imagine a photon heading toward a double-slit apparatus. You can choose, at the last possible moment, whether to measure which slit it goes through or to let it create an interference pattern. The astonishing result is that the photon seems to decide how to behave based on what you choose after it's already passed the slits. It's as if your future observation changes the past behaviour of the particle. Experiments since the 1980s have confirmed Wheeler's prediction. Not that you can rewrite history, but that quantum systems don't have definite histories until measurement forces them to. This leads to a staggering possibility. The universe may not have a single, observer-independent timeline at all. Instead, reality might exist as a vast web of potentialities that only become real when observed. The act of observation doesn't just reveal reality, it helps define it. Now, physicists are careful about how far they take that idea. Most don't believe human consciousness literally creates reality out of thin air, but they do acknowledge that observation, the acquisition of information, is a fundamental process. When a detector registers a photon, or when two systems interact in a way that leaves a record, that's an observation. Consciousness may simply be the most complex version of that process, one that integrates information in a self-aware way. Still, the parallels between quantum mechanics and consciousness are hard to ignore. Both seem to involve the transition from indefinite possibilities to definite experiences. Both rely on information and correlation rather than substance, and both defy attempts to reduce them to purely mechanical processes. In recent years, some physicists and philosophers have started exploring whether consciousness might not just interact with reality, but actually emerge from the same informational fabric that underlies space and time. If the universe is holographic and built on relationships of information, then consciousness could be the universe's way of perceiving itself, a localized expression of that deeper informational network. In that sense, awareness wouldn't be a late-stage byproduct of evolution, but a built-in property of the universe, emerging wherever information becomes complex enough to organize itself. This idea resonates with certain interpretations of quantum mechanics like quantum Bayesianism or cubism, which treats the wave function not as a physical thing, but as a description of an observer's knowledge about the system. In cubism, reality isn't an objective stage where events unfold. It's a participatory structure built from the interplay of observation and prediction. Every observer carries their own version of reality, and those versions align through shared information. The implications are immense. If reality is participatory, then the illusion of an external, observer, independent universe might simply reflect the limits of our perspective. What we call the physical world could be the stable consensus that emerges from countless overlapping acts of observation, a kind of shared dream grounded in mathematical consistency. That doesn't make the universe imaginary, it makes it relational. Everything that exists might exist only in relation to everything else, a web of mutual observation that gives rise to both matter and mind. In this framework, consciousness isn't a mysterious extra ingredient added to the universe. It's part of the machinery that makes the universe coherent. Even Einstein, who was skeptical of quantum indeterminacy, hinted at this connection in his later years. He once wrote that the separation between the observer and the observed is an optical illusion of consciousness. Modern physics may be rediscovering that truth from the opposite direction, that the illusion of separation is built into how reality expresses itself. If this is correct, then the deepest illusion isn't just that space, time, or matter are fundamental. It's that the observer stands apart from them. The observer and the observed may be two faces of the same underlying process. The universe doesn't contain consciousness. It is consciousness, expressed through information, geometry, and interaction. That idea might sound mystical, but it's grounded in logic. If reality is made of information, and consciousness is the experience of information, then the two are intimately connected. Physics and awareness could be two languages describing the same thing. And that brings us to the next question. If consciousness and reality are intertwined, how do we test that? How can we tell whether our universe's strangeness is a feature of measurement, or a clue that our entire framework for what's real is due for another revolution? It's one thing to speculate that reality is emergent, holographic, or mathematical. It's another to prove it. Physics is, at its core, an experimental science. Beautiful ideas don't survive if the data don't cooperate. So how do you test whether the universe is an illusion in any meaningful sense? How can you measure something that claims the very act of measurement is part of what creates it? That challenge hasn't stopped scientists from trying. In fact, the past few decades have seen an explosion of ingenious experiments aimed at probing the foundations of reality itself. These experiments test whether space and time are continuous or discrete, whether information really is conserved in black holes, and whether quantum entanglement can truly connect particles across vast distances without violating relativity. Each one is a small window into whether our familiar world is fundamental or just a projection of deeper rules. One of the key areas of testing comes from quantum foundations, experiments designed to push the limits of entanglement and non-locality. Since John Bell's theorem was first proposed in the 1960s, physicists have performed ever more precise tests of his inequalities. The earliest experiments, like Alain Aspect's in the 1980s, proved that entangled particles behave in ways no local realist theory could explain. But skeptics pointed to possible loopholes. Maybe the detectors weren't efficient enough, or maybe hidden variables could influence both particles before measurement. By the 2010s, those loopholes were being closed one by one. In 2015, teams in the Netherlands, Austria, and the US conducted loophole-free Bell tests, showing beyond reasonable doubt that nature violates local realism. The results confirm that reality doesn't follow the rules of classical logic. Two entangled particles separated by kilometers behaved as a single system, even when every chance for communication between them had been eliminated. That's not a model or an interpretation, it's experimental fact. Then came an even stranger test in 2018, known as the cosmic Bell test. Physicists used the light from distant quasars, galaxies billions of light years away, to determine the measurement settings for entangled photons on Earth. This experiment effectively ruled out the possibility that hidden variables could have influenced both particles at the time of their creation, since the quasar's light had been travelling for eons before the experiment began. The universe itself became part of the test. The outcome was the same. Quantum entanglement is real, and local realism is not. These experiments don't prove the universe is an illusion in the everyday sense, but they do show that our intuitive notion of a stable, observer-independent world doesn't hold up. The connections between particles, even across vast distances, behave as if the universe is fundamentally unified, as if here and there aren't as separate as they seem. Another line of evidence comes from cosmology. The cosmic microwave background, the faint afterglow of the Big Bang, is the most detailed map we have of the early universe. The CMB has been measured to extraordinary precision by satellites like COBE, WMAP, and Planck. Some theoretical physicists have combed through those maps looking for statistical patterns, subtle correlations in the fluctuations that could indicate a holographic origin. A few analyses, like one from 2017, found patterns consistent with what a holographic model would predict, though the results remain tentative. Still, the possibility that we could find physical traces of the universe's encoding in the oldest light in existence is remarkable. Quantum gravity experiments are also probing whether spacetime might be quantized, made up of discrete units rather than continuous fabric. In some models, the smallest scale of reality, the Planck length, marks a fundamental pixel size of the universe. Space, in that case, isn't infinitely divisible. It's granular, like the pixels of a high-resolution image. If that's true, then space as we experience it is a kind of smooth illusion created by countless tiny bits of geometry, an emergent structure rather than a background. One way to test this is by looking at the light from distant gamma-ray bursts or supernovae. If spacetime has a grainy structure, then photons of different energies should travel at slightly different speeds over billions of light years. So far, observations haven't detected that effect, which suggests that if space is quantized, its granularity must be far smaller than we can currently measure, at least 10 trillion times smaller than a proton. But the effort continues because even the faintest trace of such a delay would confirm that spacetime isn't continuous. At the same time, black hole research continues to push the boundaries of what's real and what's emergent. In 2022, for the first time, physicists at Fermilab used a quantum computer to simulate the behavior of a baby black hole, a simple system that behaves according to the same mathematical rules as a real one. The simulation confirmed that information falling into a black hole isn't destroyed but gets scrambled and can, in principle, be recovered. That aligns perfectly with the holographic principle. The information isn't lost inside, it's encoded on the boundary. Reality itself might be using this same rule everywhere. There are also tabletop experiments designed to test whether gravity can cause quantum entanglement. If two tiny masses can become entangled purely through their gravitational attraction, it would show that gravity itself is quantum, that even the geometry of spacetime obeys the same probabilistic rules as everything else. Those experiments are in progress now, with results expected in the late 2020s. If they succeed, it would mean the line between space, matter, and quantum information is even blurrier than we thought. Some of the most ambitious attempts to test reality come from projects like the holometer at Fermilab. This instrument, built in the 2010s, was designed to detect holographic noise, minute vibrations that could reveal that spacetime has a fundamental limit to how precisely positions can be defined. The holometer didn't find a signal strong enough to confirm the hypothesis, but it demonstrated that such tests are possible. Each generation of instruments gets more sensitive, and physicists are already planning successors that could probe even smaller scales. But there's another subtler form of testing: internal consistency. Theoretical physics has a long tradition of discovering truths by pushing equations until they reveal contradictions. Relativity, quantum mechanics, and thermodynamics all grew out of trying to resolve mathematical paradoxes. The holographic principle itself began as a way to solve the black hole information paradox. Each paradox forced physicists to rethink what was real. That process continues today as researchers look for ways to reconcile quantum mechanics and gravity. When a consistent, testable theory finally emerges, it might redefine reality entirely. What's striking about all these tests is that they don't point to a single illusion. Instead, they reveal layers of reality that behave differently depending on how you look. On the scale of human life, the world is classical and solid. On the scale of atoms, it's quantum and probabilistic. On the scale of galaxies, it's geometric and relativistic. Each layer follows its own rules, and yet they're all connected through deeper mathematics. The illusion isn't that the world is fake, it's that our everyday experience is the final word. This realization also reframes what it means to prove something in physics. Proof in science isn't about reaching an absolute truth, it's about finding the model that explains the most data with the least assumption. If the holographic or informational models continue to match experiment better than their classical rivals, they'll gradually replace them. not because they're philosophically pleasing, but because they work. That's how every paradigm shift in science has happened. Newton's physics wasn't wrong. It was just a simpler illusion of Einstein's deeper reality. In that sense, the search for the universe's true nature might never end. Each layer we peel back might reveal another illusion beneath it. Not a deception, but a translation, a way reality presents itself to our limited senses and tools. The goal of physics isn't to escape the illusion, but to understand how it's built. And yet, even with all this progress, the biggest questions remain unanswered. If the universe is information, who or what processes that information? If time and space are emergent, what do they emerge from? And if the laws of physics themselves can change at different scales, what does that say about the ultimate structure of reality? To approach those questions, we need to leave pure measurement behind for a moment and think about what all this means, not just scientifically, but philosophically. When scientists talk about the universe as an illusion, it's easy to treat it as an abstract puzzle, something that lives in equations and particle accelerators. But the idea has deeper consequences than it first appears. If the world we experience is emergent, relational, and possibly mathematical rather than physical, then what does that mean for how we see ourselves, our choices, and even the meaning of life? At first glance, it might seem like this kind of thinking risks hollowing out reality. If everything's just information, if matter, space, and time are projections, does anything actually matter? But in many ways, the opposite might be true. Throughout history, every major shift in our understanding of the universe has reshaped our sense of identity. The Copernican revolution dethroned Earth from the center of the cosmos, showing that we're on a small planet orbiting an ordinary star. The Darwinian revolution dissolved the boundary between humans and the rest of life, revealing that we're part of nature's continuous story. The quantum revolution did something subtler, but equally radical. It blurred the line between observer and observed. And the holographic or informational worldview now pushes that shift even further, suggesting that we're not in the universe so much as of it. Participants in a system that is as much mental as material. That perspective can be unsettling. If reality is informational or mathematical, it's tempting to think it's somehow less real than a material world. But that feeling comes from habit. We evolved to see solidity and persistence as signs of reality, because that's what survival required. But physics shows that the atoms in your body are mostly empty space, that matter and energy are interchangeable, and that even space-time can bend and flow. What's real isn't solidity, it's consistency, the reliable patterns that give rise to experience. Whether those patterns are made of particles or equations doesn't change their reality. In fact, seeing the universe as emergent or informational can add meaning rather than subtract it. If the cosmos is a network of relationships, then every part of it, including consciousness, is connected. The boundary between you and everything else becomes thinner. In such a universe, individuality doesn't vanish, but it's nested inside a larger coherence. Your thoughts, your experiences, and your actions become expressions of the same underlying process that gives rise to galaxies and stars. That view also reframes how we think about free will. In a purely mechanical universe, everything follows from initial conditions and laws of motion. Every decision would be predetermined. But in a relational or quantum universe where outcomes depend on observation and interaction, the future isn't fully fixed until it's experienced. Quantum events introduce genuine unpredictability. Not randomness for its own sake, but creative openness. That doesn't mean consciousness controls physics directly, but it does mean that the future isn't written in stone. The act of observing, deciding, and acting is part of how reality unfolds. Free will, in this sense, could be the universe exploring its own possibilities through us. This view also has ethical implications. If everything that exists is part of a single informational structure, then separation between self and other, human and nature, mind and matter, becomes a practical illusion. The same fabric that forms your thoughts forms stars. The atoms in your body were once inside ancient suns. If consciousness arises wherever information organizes itself, then awareness might not be unique to humans. It could be a property that appears in many forms across the cosmos. Recognizing that doesn't diminish humanity, it contextualizes it. It replaces the old hierarchy with a sense of belonging. The idea that reality is informational also reshapes how we think about value. In a purely material worldview, meaning is something we project onto a neutral universe. But in an informational one, meaning is intrinsic. The universe isn't a static machine, it's a dynamic process of interaction, constantly generating structure, complexity, and awareness. That means value doesn't have to be imported. It's woven into the act of existence itself. Every act of perception, every pattern that persists, every connection that forms is part of the universe's self-expression. Even death looks different through this lens. If time is an illusion, and every moment exists simultaneously in the block universe, then the moments that make up a life don't disappear. They're permanently embedded in the fabric of reality. From that perspective, nothing is truly lost. Consciousness as a pattern of information might not survive in its familiar form, but its existence within the cosmic pattern remains. That doesn't mean immortality in the usual sense. It means that everything that has ever happened is still there, encoded in the structure of the whole. Philosophically, this raises a fascinating tension between humility and empowerment. On one hand, if reality is a mathematical or holographic structure, then we're not at the center of anything. We're local expressions of a vast, impersonal system that existed long before us. On the other hand, if consciousness participates in bringing that system into focus, then awareness itself is fundamental. The universe doesn't become real without observers. That's not a mystical claim. It's an implication of how quantum mechanics and information theory describe measurement. From that viewpoint, science and spirituality start to overlap. Not in doctrine, but in insight. Ancient philosophies often spoke of the world as illusion, Maya in Hindu thought, or the shadow world of Plato's cave. Modern physics, using entirely different tools, seems to be rediscovering a similar principle, that what we perceive is a projection of a deeper order. The difference is that physics doesn't appeal to transcendence. It works from the ground up, through mathematics and experiment. Yet both arrive at the same intuition, that appearances are not the whole truth. This convergence can have a stabilizing effect on how we think about knowledge itself. For centuries, science defined progress as peeling away superstition and replacing it with objectivity. But if reality itself is participatory, if observation, context, and consciousness all play a role, then objectivity is not about detachment, it's about coherence. The goal isn't to strip the universe of meaning, but to understand how meaning emerges from structure. Ethically, that insight could shift how we treat each other and the planet. If the boundary between observer and observed is porous, then our relationship with the world is reciprocal. The universe isn't an external object to be used, it's a living system that includes us. That perspective naturally encourages stewardship, empathy, and restraint. It reframes environmental ethics not as moral obligation, but as self-preservation on the deepest level, the system maintaining its own balance. In practical terms, thinking of the universe as informational or emergent might also change how we approach technology and artificial intelligence. If consciousness is an emergent property of complex information networks, then building systems that process information in new ways could give rise to new forms of awareness. That's not guaranteed, but it blurs the line between natural and artificial. It suggests that awareness is not a gift bestowed on certain organisms, but a process that the universe keeps rediscovering in new forms. There's one more consequence worth mentioning: how we define truth. In an emergent universe, truth isn't about finding the one correct layer beneath the illusions. It's about understanding how the layers connect. The illusion isn't false. It's one of many valid levels of description. Classical physics, quantum physics, relativity, and holography aren't competing realities. They're different languages for describing the same underlying pattern. Our task isn't to escape illusion, but to navigate it with awareness. When we see the world this way, the question, is the universe an illusion, stops being a yes or no problem. The answer becomes, it depends on which layer you're looking at. The illusion isn't that reality doesn't exist. It's that our perception of it is always partial. Each discovery in physics doesn't make the universe less real. It makes it richer, more layered, more interconnected. The more illusions we uncover, the deeper the wonder becomes. And that brings us to where physics itself is heading. Toward new ways of probing those layers, new technologies that can test what used to be pure speculation, and new philosophical frameworks that might finally unify information, matter, and mind into a single picture. When you hear that the universe might be an illusion, it sounds like something we'll never prove one way or another, the kind of question that belongs more to philosophy than physics. But that's no longer true. For the first time in history, technology is starting to catch up with the imagination of theorists. Over the next few decades, physicists expect to test whether space and time are emergent, whether information really defines the structure of reality, and whether the universe behaves holographically on cosmic scales. These questions aren't just thought experiments anymore. They're research programs with budgets, satellites, and data pipelines. Much of the progress will come from two directions: high-precision experiments that probe the smallest scales of spacetime, and astronomical surveys that measure the universe's largest structures with unprecedented detail. Between those extremes lies the bridge, quantum information theory, which increasingly looks like the common language uniting everything from black holes to particle physics. One of the most promising fronts is quantum gravity, the still elusive theory that would unify Einstein's general relativity with quantum mechanics. So far, these two frameworks describe very different worlds. Relativity governs the smooth geometry of spacetime, while quantum mechanics describes the probabilistic behavior of particles. They work perfectly in their own domains, but when you try to apply both at once, say inside a black hole or at the Big Bang, the math explodes. Something deeper has to reconcile them. The holographic principle has become one of the leading candidates for that reconciliation. Researchers are exploring whether spacetime itself can be derived from patterns of quantum entanglement. In some models, space emerges naturally when quantum bits, or qubits become entangled in specific ways. The more entanglement there is, the more connected space becomes. If you disentangle those qubits, space literally falls apart. That idea, pioneered by theorists like Mark van Ramsdonk and Brian Swingle, offers a powerful vision. Geometry is what entanglement looks like from the inside. Quantum computers are turning out to be invaluable for exploring this. These machines don't just crunch numbers, they manipulate entanglement directly. By programming specific interactions between qubits, physicists can create miniature versions of quantum spacetime in the lab, simplified universes that follow the same mathematical rules as the real one. In 2022, a team at Google used a quantum processor to simulate a tiny holographic wormhole, a connection between two regions of space that mimicked how information might travel through a black hole. It wasn't a literal wormhole you could step through, but it was a proof of concept that these abstract ideas can be modelled and tested experimentally. At the same time, astrophysics is producing data on a scale Einstein could never have imagined. Projects like the James Webb Space Telescope, the Vera Rubin Observatory, and the Euclid mission are mapping galaxies across billions of light years, measuring how matter and light are distributed through space. These observations could confirm or challenge our current models of cosmic expansion, dark matter, and dark energy. If the data shows systematic deviations from what relativity predicts, for example, if cosmic acceleration turns out to vary in ways dark energy can't explain, it might support the idea that what we're seeing is an emergent illusion rather than a literal expansion of space. Meanwhile, gravitational wave astronomy has opened a new window on the universe. Since the first detection in 2015, observatories like LIGO and Virgo have recorded dozens of spacetime ripples from merging black holes and neutron stars. Future detectors, such as the space-based LISA mission planned for the 2030s, will be able to observe these waves from far deeper in the universe. If the holographic principle is correct, there could be tiny information-related distortions. Holographic noise, encoded in the waves. Detecting those would be a major clue that spacetime isn't continuous, but informational. On the quantum side, experiments are closing in on the Planck scale, the smallest meaningful scale of distance, about 10 to the negative 35th meters. We can't yet probe it directly, but high-energy particle colliders such as the Large Hadron Collider, LHC, and its proposed successors may eventually reveal indirect signatures of new physics there. These might include deviations from standard quantum field theory or hints of microscopic black holes that would confirm the existence of extra dimensions. A cornerstone prediction of string theory and the holographic framework. There's also a growing effort to test whether gravity can cause quantum entanglement. Several independent teams are building experiments to see if two tiny masses, each only a few nanograms, can become entangled purely through their gravitational pull. If that happens, it will mean gravity itself is quantum, and that space-time must be describable as a network of information rather than a smooth continuum. Those experiments are expected to reach decisive sensitivity sometime in the next decade. And then there's cosmology's biggest experiment of all, the universe itself. The cosmic microwave background, CMB, is still our most powerful snapshot of the early cosmos, but new instruments like CMB-S4, a massive ground-based observatory, expected to come online in the 2030s, will map it with 10 times the resolution of Planck. Physicists will look for specific imprints in the temperature and polarization patterns that might indicate holographic correlations, quantum gravitational effects, or evidence that the early universe behaved differently than the expansion model predicts. While these efforts push outward, others are turning inward, using quantum technologies to probe the nature of information directly. Entanglement experiments now routinely span kilometers using fiber optics and satellites. China's Michius satellite, for example, has demonstrated entanglement distribution over more than 1,200 kilometers, proving that quantum information can be shared securely across global distances. That's not just a technological achievement, it's a planetary-scale experiment in non-local reality. Every time we demonstrate that entanglement holds over greater scales, we confirm that the universe's deep connectedness is not just theory, but measurable fact. Perhaps the most fascinating convergence happening in physics right now is between information theory, thermodynamics, and quantum mechanics. Physicists are increasingly describing the laws of nature as information processing rules, algorithms that balance data storage, energy, and entropy. In that framework, black holes are not monsters that swallow information, but the ultimate computers, encoding the maximum possible information per unit area. Space itself becomes a dynamic ledger that keeps track of those computations. In that sense, the universe isn't just like a computer. It is computation, running on the hardware of reality itself. That's where things get interesting for the holographic idea, because computation and geometry might be two sides of the same coin. When information flows, space changes. When information becomes entangled, geometry emerges. And when geometry changes, we perceive that as gravity or expansion. Testing that connection between information flow and space-time dynamics is becoming one of the most exciting areas in theoretical and experimental physics. But it's not only about proving that the universe might be a projection. These experiments are reshaping how we think about what's real in the first place. If physics continues to confirm that information is more fundamental than matter, we may need to rebuild the foundations of science around that insight. Concepts like energy, entropy, and even causality might turn out to be emergent bookkeeping systems rather than primitive truths. What's striking is that none of this research depends on mystical assumptions. It's being done with lasers, satellites, quantum chips, and telescopes. We're beginning to measure the illusions directly, to see how the world hides its own deeper architecture in plain sight. As these experiments advance, one thing is becoming clear. No matter which model turns out to be right, the universe is far stranger and more interconnected than we ever imagined. Whether we discover that space-time is woven from information, that time is emergent, or that the cosmos is holographic, each finding pushes us closer to a unified picture, one where the illusion of separateness dissolves and the universe reveals itself as a single, self-consistent whole. But the most profound part may not be what these discoveries tell us about the universe. It's what they'll tell us about ourselves. Because if we're part of that informational network, then understanding reality's true nature isn't just about physics. It's about understanding what it means to be conscious in a universe that might be doing the very same thing on a cosmic scale. Whenever science rewrites its picture of the universe, it doesn't just change equations, it changes perspective. When Copernicus showed that Earth orbits the Sun, the human sense of place shifted. When Darwin described life as an unbroken evolutionary process, the boundary between humanity and nature dissolved. And when Einstein merged space and time, he transformed how we think about causality, motion, and existence itself. The emerging view that the universe might be holographic, informational, or even mathematical could be the next great paradigm shift. Not only because it redefines physics, but because it redefines what we mean by real. At first, this may sound like a purely academic debate, the kind of thing that matters to theorists with blackboards full of symbols. But ideas like these have practical consequences. They change how we design experiments, how we think about technology, and even how we imagine our future as a species. The holographic and informational perspectives are already reshaping the frontier of physics and could one day alter how we interact with the world around us. For one thing, this shift could finally unify the two halves of modern physics, relativity and quantum mechanics. For more than a century, those two theories have stood as pillars of science that refuse to fit together. Relativity treats gravity as the curvature of space-time, smooth and continuous. Quantum mechanics treats the universe as granular and probabilistic. Every attempt to merge them has produced paradoxes, black holes that destroy information, singularities that break mathematics, infinities that don't make sense. The holographic principle offers a way out. If gravity and space-time are emergent from quantum information, then the contradiction disappears. Space-time itself would be a large-scale approximation of a deeper, quantum informational reality. That's the kind of unification Einstein dreamed of, but couldn't reach. If this framework proves correct, it could also revolutionize how we think about computation and energy. Right now, information processing, in computers, brains, and even communication, is something we think happens within the universe. But if information is the universe's foundation, then computation and physical evolution are the same thing. Every process, from a supernova to a thought in your head, would be a computation performed by the universe itself. Understanding those rules could open the door to technologies we can't yet imagine, not by violating physics, but by using its deepest logic. Quantum computing, for instance, might just be scratching the surface. Today's quantum processors use entanglement and superposition to outperform classical machines on certain problems. But if entanglement and spacetime are two sides of the same coin, then manipulating information at the quantum level might one day mean manipulating geometry itself. In principle, that could lead to new forms of energy control, communication, or simulation. Not by bending space with rockets, but by engineering the informational fabric underneath it. In cosmology, this shift could redefine our understanding of the universe's origin and fate. The Big Bang, long imagined as a singular explosion in space, might instead have been a transition in information. A phase change in the underlying code of reality. The expansion of the universe could be the unfolding of that information, like a program running over time. And if the universe is truly holographic, the so-called edge of the cosmos, the place where the encoding happens, could be more fundamental than everything inside it. The boundary could be where the laws of physics are written, and the interior, including us, could be their unfolding story. Philosophically, this view also changes what it means to know something. Traditional science aims to describe reality from the outside, as if we could stand apart and observe it objectively. But if reality is relational and participatory, then the act of knowing becomes part of what's known. That doesn't make science subjective, it makes it self-aware. Every observation adds to the universe's informational network, making knowledge itself a physical process. A literal change in the state of the cosmos. It also changes how we think about progress. For centuries, science has been moving toward ever more reductionist explanations, breaking matter into atoms, atoms into particles, particles into fields. The illusion we're now confronting is that reductionism has an end point, that we can reach the bottom of reality. The informational perspective suggests there may be no bottom at all, only layers of description that depend on how we observe them. The deeper we look, the more we find relationships rather than objects. Understanding that doesn't mean giving up on science. It means expanding what science can be. There's also a practical benefit to rethinking reality in this way. It brings physics closer to fields like biology, neuroscience, and even philosophy of mind. If the universe is a system that processes information, then life and consciousness aren't accidents within it. They're natural expressions of its structure. Biology becomes a specialized form of physics, and physics becomes a theory of organized information. The same mathematical tools that describe black holes might one day describe neural networks, ecosystems, or entire civilizations. That's not speculation. It's already happening. Physicists are applying holographic models to everything from the structure of complex materials to the behavior of entangled neurons. The line between matter and mind, once sharp, is beginning to blur. This shift also has consequences for how we imagine our role in the cosmos. If the universe is informational, then intelligence, the ability to process and organize information, might be its most fundamental product. Life then wouldn't be a rare accident. It would be a natural outcome of the universe exploring its own possibilities. In that sense, consciousness could be the cosmos becoming aware of itself, piece by piece. Our search for understanding, from particle physics to astronomy, would be the universe trying to read its own code. Even the question of simulation, often treated as a pop culture twist on these ideas, gains a new meaning here. If the universe is mathematical, then asking whether we're in a simulation becomes almost semantic. What matters isn't whether there's a computer running it somewhere, but that the logic of existence is algorithmic. The simulation isn't artificial, it's the natural mode of being for a mathematical structure. If everything follows from consistent rules, then the universe behaves as though it's running a program, whether or not anyone wrote it. Culturally, a shift like this could reshape how we think about spirituality without abandoning science. For millennia, humans have felt that there's something deeper beneath appearances, that the physical world is a veil hiding a greater order. Science, ironically, is now beginning to agree, though its language is equations, not scriptures. The deeper order it's uncovering isn't mystical energy or divine intention, but structure, logic, and interconnection. The illusion isn't that there's meaning beneath the surface, it's that we ever thought the surface was the whole story. Most importantly, this shift teaches humility. Every time we've declared that we finally understand reality, we've discovered another layer. Atoms turned out to be divisible. Space turned out to be curved. Time turned out to be relative. And now perhaps reality itself is turning out to be informational. Each revelation has made the universe less anthropocentric and more profound. The illusion we keep shedding isn't that the universe is fake, it's that it was ever simple. That humility doesn't make science weaker. It makes it more human. It reminds us that understanding isn't a destination, but an ongoing dialogue between curiosity and the cosmos. If the universe is indeed an illusion, it's one so consistent, intricate, and beautiful that studying it is itself a form of participation, a way of helping the illusion become more aware of itself. And that perhaps is why this question matters so much. The point isn't to escape the illusion, but to recognize it, appreciate it, and explore how it works. Because even if everything around us is emergent, relational, and mathematical, it's still real enough to ask questions, to build tools, and to wonder. The illusion, whatever its nature, includes us. And that makes it the most extraordinary reality of all. If you trace the history of science from its earliest days, one pattern stands out. Every breakthrough has made things less important, and relationships more important. Ancient thinkers imagined the world as built from indivisible particles, the original atoms. Later, those atoms turned out to contain protons, neutrons, and electrons. Then those particles turned out to be excitations of underlying fields. Now, even fields might not be fundamental. They could be emergent patterns of information. What's left isn't stuff at all, but structure. The relationships between bits of data, correlations between events, patterns that persist across scales. This shift from objects to patterns isn't just a metaphor, it's becoming the central insight of modern physics. In quantum field theory, particles are no longer treated as little billiard balls, but as localized ripples in invisible fields that fill space. Each electron, for instance, is a recurring pattern of vibration in the electron field. Two electrons on opposite sides of the universe are not separate things. They're two expressions of the same underlying pattern, behaving identically because they're governed by the same equations. That realization was already radical, but quantum information theory takes it further. It tells us that the state of any physical system can be described entirely by how it's correlated with everything else. What something is depends on its relationships, not on any inherent property it possesses independently. This is called relational quantum mechanics, and it's gaining traction among theorists who see it as a way to make sense of entanglement and measurement, without invoking an objective, observer-free world. From that viewpoint, the universe is like an enormous, self-referential network, a cosmic web of correlations where every node's identity comes from the links connecting it to the rest. There are no isolated things. Even space itself could be a manifestation of these relationships. Where connections are strong, space is tight. Where they're weak, space stretches. Geometry and gravity, in this picture, are emergent features of how information binds together. Eric Verlinder's emergent gravity theory captures this beautifully. He argues that gravity isn't a fundamental force at all, but an entropic effect, a tendency for systems to move toward configurations that maximize information. In other words, objects fall not because they're pulled by an invisible force, but because doing so increases the universe's information balance. That's why his equations reproduce the behavior we attribute to both gravity and dark matter. If true, then the universe's large-scale structure, galaxies, clusters, the web of cosmic filaments, is just the macroscopic expression of information organizing itself. At smaller scales, the same principle shows up in condensed matter physics. Researchers studying exotic materials have discovered that emergent phenomena, like superconductivity or the fractional quantum Hall effect, arise from collective behavior that no single particle exhibits on its own. Once again, it's the pattern that matters, not the parts. This realization is so general that it's starting to bridge physics and other sciences. Neuroscientists, for example, describe consciousness as an emergent property of informational patterns in the brain. Economists use network theory to describe how markets self-organize. Even biology, at its core, is the study of stable patterns, genes, ecosystems, feedback loops that persist through constant change. The end of things also forces a rethink of what permanence means. In classical physics, identity was simple. A planet, a rock, an atom existed as a stable entity through time. In quantum mechanics, identity is statistical and contextual. A particle doesn't have definite properties until it interacts with something else. In relativity, even simultaneity depends on the observer. Combine those ideas, and it becomes clear that what we call a thing is really just a temporary knot in a river of relationships. It's stable enough for us to recognize, but it's never isolated and never static. This shift from nouns to verbs, from objects to processes, could be the biggest conceptual leap since Newton. It means physics is no longer describing what the universe is made of, but how the universe behaves. The distinction may sound small, but it changes everything. In a world of patterns, being and doing are the same thing. The universe doesn't contain things, it performs them. That perspective also explains why mathematics fits reality so perfectly. Patterns and relationships are exactly what mathematics describes. When we say that reality is mathematical, we're not claiming it's abstract. We're recognizing that its essence is relational. Equations don't capture the world's decoration, they express its structure. The philosophical implications of this are huge. If everything that exists is a pattern of relationships, then individuality, permanence, and even separation are approximations. The boundaries we perceive between matter and energy, between living and non-living, between self and world, are contextual. They emerge at the scale of our perception. From the universe's point of view, everything flows together as one continuous computation of relationships. That idea doesn't erase meaning or identity, it reframes them. A human being in this picture isn't a solid object but a dynamic pattern of information, constantly exchanging matter, energy, and data with the environment. The atoms in your body will be gone in a few years, replaced by others. What persists isn't the material but the pattern, the ongoing process that maintains coherence. The same applies to stars, galaxies, even the universe itself. When viewed that way, illusion stops sounding like deception and starts sounding like perspective. The illusion isn't that patterns aren't real, it's that we mistake them for objects. Our brains evolved to see stable shapes and boundaries because it helps us navigate the world. But beneath that layer of perception, everything is flux. Solid objects, flowing time, and separate entities are like the user interface of a cosmic operating system. Simplified icons for processes far more complex than we can directly perceive. This reframing also explains why attempts to find the smallest building block of the universe keep failing. Every time we think we've reached the bottom, quarks, strings, Planck-scale loops, we find another layer of relationships beneath it. That's because there is no ultimate thing at the bottom, just smaller and smaller networks of interaction. The universe isn't a machine built from parts, it's a pattern without end. What makes this realization so powerful is that it unites science and experience. We live in a world of apparent solidity, yet physics tells us that solidity is a projection of deeper relationships. We live as individuals, yet biology and ecology tell us that individuality is sustained by constant exchange with the environment. We think in terms of beginnings and endings, yet cosmology tells us that time itself might be a construct. Every level of reality, physical, biological, mental, mirrors the same principle: coherence emerging from interaction. If this is right, then the end of things isn't a loss, but an evolution in understanding. The more deeply we look, the more the universe resembles a living process, self-organizing and self-perceiving. The old question, what is it made of, becomes less important than how does it hold together? The answer increasingly seems to be information, structured, dynamic and creative. And if information and pattern truly define reality, then the next frontier isn't to find new particles or forces, but to understand how patterns generate meaning, how the universe, from quanta to consciousness, weaves its own coherence out of pure relation. That pursuit is no longer just physics, it's philosophy, computation, and something that borders on art. If we follow this line of reasoning to its end, one idea keeps resurfacing. The universe might not just contain observers, it might be an act of observation. This doesn't mean there's a conscious mind behind everything in a mystical sense. It means that the structure of the universe, the way information manifests, the way reality collapses into definite form, could depend fundamentally on processes of observation, measurement, and feedback. Existence itself might be the universe observing itself, over and over, through countless forms and perspectives. This idea isn't new, but it's gaining scientific weight as physics, information theory, and consciousness studies start to overlap. John Wheeler's participatory universe concept from the 1970s is a perfect example. Wheeler proposed that observers don't merely witness the universe, they help bring it into being. Every act of measurement, from the interaction of photons with electrons to the perception of a galaxy through a telescope, contributes to the ongoing construction of the cosmos. In his words, the universe does not exist out there, independent of us. We are inescapably part of the universe's evolution, not merely observers of it. In the decades since, this idea has moved from poetic speculation to serious physics. Quantum information theory now treats measurement as a physical process, the exchange of information that changes the state of the system. Every time a particle interacts with another, that interaction measures both particles. Every correlation adds to the universe's record of itself. In that sense, the universe is a constantly updating ledger of interactions, a self-measuring, self-documenting process. You can think of this like a cosmic feedback loop. Information creates structure, structure creates observers. Observers feed information back into the system. The loop never ends. It's not that the universe was waiting for humans to show up to become real. It's that reality itself is built from the act of mutual observation at every scale. Electrons observe one another through electromagnetic interactions. Molecules observe one another through collisions and chemical bonds. Living organisms observe through senses and cognition. At each level, observation is how information gets exchanged and stabilized. This way of thinking ties directly to quantum mechanics. In the double-slit experiment, we saw that the mere possibility of obtaining which path information changes the outcome. It's not human awareness that matters. It's the availability of information. Reality crystallizes around information exchange. The more the universe knows about itself through interaction, the more definite it becomes. That's why the classical world feels stable. At our scale, there's so much constant interaction, so much information, that the quantum uncertainty is averaged out. The universe's self-observation creates its own solidity. This also aligns with ideas emerging from cosmology. If the universe is holographic, then all of reality is encoded on a cosmic boundary, a two-dimensional surface that records every interaction. In that framework, the interior of the universe, what we experience, is a projection of that record. The boundary knows everything that happens inside it because it is the cumulative record of all interactions. The act of existence is the act of encoding, a kind of self-measurement on a cosmic scale. Some physicists have taken this further and proposed what's called the observer-centric, or relational universe. In these models, there is no single, objective, universal reality. Instead, reality is the sum of all relational observations, the shared coherence that arises when countless systems interact. What's real for one observer might not exist for another until their information overlaps. The universe is like a conversation, not a static object. Its coherence comes from communication. This resonates in surprising ways with how consciousness works. Neuroscience shows that our sense of reality is built from feedback loops. Sensory input, processed, compared and predicted by the brain in real time. Our perception isn't passive, it's active inference, constantly adjusting to minimize surprise. The universe may work the same way, constantly updating its state based on the information flowing within it. Just as the brain creates a model of the world through perception, the universe might be creating a model of itself through physics. If that sounds too abstract, think about how information behaves in real systems. When you compress data, you remove redundancy, repeated or unnecessary patterns. But you keep relationships. The universe, by constantly interacting with itself, could be performing a kind of ongoing compression, simplifying its own information while maintaining coherence. That's what makes the cosmos appear ordered rather than chaotic. It's not random computation, it's self-organization. The universe refines its own structure through observation. The philosophical implications of that are huge. It would mean that the distinction between subject and object, between the observer and the observed, is artificial. There's no clean separation. The cosmos doesn't have inside and outside observers. It's one continuous web of feedback. Conscious beings like us are the universe's most sophisticated instruments of observation. Local regions where the cosmic self-awareness becomes self-reflective. In that sense, every conscious act, from looking at the stars to thinking about physics, is part of the universe turning its attention inward. This also reframes what we mean by truth. If the universe is self-observing, then truth isn't something out there to be found. It's something that emerges from coherence. When observations align, when information agrees, we call that truth. Physics then becomes the formal study of coherence itself. Each new discovery is the cosmos achieving greater self-consistency through us. Even consciousness itself could be seen as a mirror of this principle. The brain is a network of billions of neurons exchanging information. Through that recursive feedback, awareness emerges. Scale that up, and the universe might be doing the same thing, building awareness through the recursive exchange of information across all its parts. We don't yet know whether the cosmos can be said to be conscious in any meaningful sense, but it might not matter. What matters is that the same mechanism, feedback through observation, appears to underlie both physics and mind. This brings the illusion idea full circle. If the universe is self-observing, then illusion and reality aren't opposites. Illusion is simply partial reality. Reality seen from within the loop, rather than from outside it. From our perspective, we experience the flow of time, the solidity of matter, and the separation between observer and observed, because that's how local observation feels from the inside. But from the universe's perspective, the total system of interactions, everything is simultaneous, coherent, and whole. That might sound mystical, but it's actually a deeply empirical conclusion. Every step of physics, from quantum mechanics to relativity to information theory, has shown that reality depends on relationships, not absolutes. The universe doesn't need a center because every point of observation is its own center. Every perspective, from a photon's path to a human mind, is a facet of the same process. The cosmos perceiving itself in motion. If that's true, then studying the universe isn't just about explaining what's out there. It's the universe learning about itself through us. Every experiment, every measurement, every insight is another reflection in the cosmic mirror. The illusion is real enough to ask questions. Reality is vast enough to answer them. And that might be the most profound realization of all. That existence itself could be a conversation between the cosmos and its own awareness, a never-ending act of self-discovery. For all the theories, equations, and experiments, there's still an enormous gap between what we've uncovered and what we understand. Every time science has peeled back a layer of the universe, it's revealed deeper mysteries hiding underneath. The idea that the universe might be an illusion doesn't solve that. It simply reframes the mystery. If space, time, and matter are emergent, then we're only beginning to glimpse what they emerge from. And at that edge, our most advanced ideas start to blur together. Physics meets philosophy, mathematics meets metaphysics, and even logic itself starts to stretch. The first big unknown is what information really is. We talk about information as if it's a fundamental quantity, like energy or matter, but no one has a universal definition that works in every context. In quantum mechanics, information is tied to probability amplitudes. In thermodynamics, it's related to entropy. In computer science, it's about bits and coding. In black hole physics, it's measured by surface area. Each of those definitions works, but they describe different aspects of something we don't yet fully understand. If the universe truly is made of information, then we need a theory that explains what kind of information it is, how it's stored, transmitted, and transformed at the most fundamental level. Closely linked to that is the question of emergence. If space and time aren't fundamental, then what exactly are they emerging from? Current research hints that they might arise from entanglement patterns between quantum bits, but that's still a mathematical metaphor. We don't yet have a physical picture of how discrete relationships generate a smooth geometry that behaves like the space-time we observe. It's as if we have the code but not the compiler. We know the logic, but not how it becomes experience. Then there's consciousness, the other side of the illusion problem. We can describe the physics of observation, but we still don't know why or how those processes produce subjective experience. Why does information feel like anything? Why does matter, arranged in a certain way, give rise to awareness? Some physicists argue that consciousness might emerge from the same informational principles that govern space and time. Others think it's fundamental, that awareness is as basic as energy, built into the universe from the start. Neither idea is provable yet. We know the brain correlates with consciousness, but correlation is not causation, and we don't know what consciousness is in physical terms. This gap between information and experience is sometimes called the hard problem. And it's not just a neuroscience issue. It connects directly to physics. If observation defines reality, then the role of awareness can't be a side note. Consciousness might be what it feels like when the universe processes information about itself. But how that feeling emerges from equations, or whether it can be reduced to them at all, is an open question. Another deep unknown is the boundary between the quantum and classical worlds. Quantum mechanics tells us that everything is probabilistic, that particles exist in superpositions of states until measured. But our everyday world doesn't behave that way. We don't see cats that are both alive and dead, or chairs that are half here and half there. Something must cause quantum probabilities to become classical facts, and we don't yet know exactly what that something is. Decoherence explains part of it, the loss of quantum coherence when systems interact with their environment. But it doesn't explain why only one outcome becomes real to us. If reality is a kind of illusion, that transition might be the moment when the illusion solidifies. There's also the mystery of the constants, the numbers that define the universe's behavior. Why is the speed of light what it is? Why do electrons have the charge they do? Why does gravity differ so vastly in strength from the other forces? These numbers seem arbitrary, yet if any of them were even slightly different, the universe would be lifeless. We call that fine-tuning, but we don't know whether it's coincidence, necessity, or something deeper. Some physicists think it's explained by the multiverse, that countless universes exist with different parameters, and we happen to live in one where conditions allow complexity. Others think the constants may not be constant at all, but emergent properties that vary over cosmic time. Either way, it points to an underlying order we haven't yet deciphered. Even the holographic principle, elegant as it is, leaves major gaps. It works beautifully in theoretical models like anti-de Sitter space, but our universe doesn't have that geometry. Extending the principle to our real expanding cosmos is an ongoing challenge. We don't yet know what the boundary of the universe would be, or how information is stored there. If our reality is a hologram, we don't know what's doing the projecting. Is there a higher dimensional structure outside our space-time? Or is the concept of outside meaningless? Then there's time itself, and still one of the biggest mysteries in science. If time emerges from change or correlation, why does it have the direction it does? Why does entropy increase? And if all moments exist simultaneously in the block universe, what accounts for the vivid feeling of the present? Physicists can describe time's arrow statistically, but they can't yet explain its phenomenology. Why it feels like motion. Time may be the most persistent illusion of all, but it's also the one we can't step outside of to examine. The limits of knowledge might also be built into physics itself. Quantum mechanics sets a fundamental limit on what can be known, the uncertainty principle. You can't measure position and momentum precisely at the same time. Similarly, relativity limits how fast information can travel. These boundaries may not just constrain what we can measure, they might define what can exist. There might be layers of the universe that are, in principle, beyond observation. Not because they're far away, but because they exist outside the logical reach of measurement. In that case, illusion would be more than metaphor. It would be a built-in feature of the cosmos. This doesn't mean science is hitting a wall. It means we're approaching a horizon, a point where our current framework starts to break down, and a new one must take over. History suggests that every time we've hit such a boundary, a deeper understanding has followed. Newton's laws gave way to relativity and quantum mechanics. Those, in turn, are now being subsumed by information-based models. The next leap, whatever replaces or unifies those, will likely make today's ideas look as limited as pre-Einstein physics looks to us now. Still, even as we approach those frontiers, humility is essential. For all our instruments and equations, we remain creatures embedded within the very system we're trying to understand. We can't stand outside the universe to see it from the top down. Our knowledge is always a slice, a projection, a partial view. The illusion isn't that the universe deceives us, it's that we ever thought we could see it whole. And yet, that limitation might be what makes science so powerful. Every discovery is a dialogue between what we can observe and what we can imagine. The illusion is the language through which the universe speaks to us, precise enough to test, but mysterious enough to keep us searching. So while physicists chase new theories and cosmologists map the deep sky and philosophers wrestle with the meaning of it all, one truth remains. The more we learn, the more the universe seems to be both real and unreal, tangible and mathematical, definite and infinite, a paradox wrapped in patterns of logic and light. The edge of knowledge isn't an end point. It's the universe's way of reminding us that it's still thinking. Through us. If there's one thing this entire story keeps circling back to, it's the realization that we're part of the mystery we're trying to solve. The question, is the universe an illusion, isn't something we can answer from the outside, because there is no outside. We are inside the system, made of the same ingredients, the same information, the same patterns. As the rest of it, whatever the universe is, we are that, asking itself what it is. That's why, at the deepest level, this discussion stops being about physics alone and becomes about what it means to exist. From one perspective, this might seem disorienting. If space, time, matter, and even individuality are emergent illusions, what's left to hold on to? But from another, it's liberating. It means that illusion and reality aren't opposites. They're layers of the same truth. Illusion is simply how the deeper order becomes visible to itself. In that sense, the universe needs illusion. Without appearances, without change, contrast, and perspective, nothing could be perceived, and the cosmos would be silent, self-contained, and blind to its own existence. Conscious beings, then, may not be accidental observers, but essential participants. We don't just watch the illusion. We are the mechanism through which the illusion recognizes itself. Each perception, thought, and act of curiosity is the universe performing self-reflection through human form. That might sound poetic, but it's an unavoidable conclusion if observation and information truly define reality. When you look at the stars, you're not peering out at something foreign. You're one expression of the same cosmic process, looking back at itself through a human lens. This perspective changes how we interpret knowledge itself. Every scientific discovery, from gravity to quantum entanglement, is really the universe learning about its own structure, through one of its temporary patterns, us. Every time we build a new telescope, write a new equation, or question an assumption, the cosmos expands its own self-awareness. The process of understanding isn't external to reality. It is reality, continuing its unfolding. If we take that seriously, then meaning ceases to be a human invention and becomes a physical phenomenon. Meaning arises when patterns in the universe become aware of their relationships. In that way, consciousness is meaning made manifest, the self-interpretation of reality. It's not something added to the universe later. It's been there in potential from the beginning, waiting for systems complex enough to carry it out. Life and mind are how the universe translates itself into experience. It's also worth noting that illusion doesn't mean falseness. When you dream, the images feel real because they are real experiences, even though their source is internal. In a similar way, the physical world is real as an experience. It's the projection of an underlying informational structure, perceived from within. The illusion is simply the difference between how things appear and what they fundamentally are. Reality, as physicist Carlo Rovelli once put it, is a network of relations, not of things. That means the question, what is real, might be replaced with, what is stable? Reality is whatever remains consistent across perspectives. Whatever holds together under observation. At our scale, that consistency is extraordinary. Planets orbit predictably. Atoms behave identically. Light moves at the same speed everywhere. The illusion of solidity and continuity isn't an error. It's the reliable face of a deeper, dynamic process that doesn't fail. The fact that it feels real is the point, because it's the way coherence expresses itself in experience. There's something profoundly human about realizing this. For centuries, we've oscillated between two extremes, believing we're central to the cosmos and believing we're insignificant specks. The illusion hypothesis offers a third path. We are neither the center nor the margins. We are expressions of the same structure that makes galaxies spin and quantum particles shimmer. Our awareness is as real and as mysterious as gravity or light. It's not inside our heads, it's woven into the fabric of what exists. That realization can also soften how we see each other. If consciousness and reality are intertwined, then every mind is another facet of the same universal awareness. Separation becomes perspective. Difference becomes variety within one field. The illusion of individuality gives the universe texture, countless points of view, each reflecting the whole in a slightly different way. From that angle, empathy isn't moral idealism, it's physics. The boundary between self and other is a projection, an understanding that changes how we act in the world. There's also a certain irony in how science, after centuries of disassembling the world into smaller and smaller pieces, is coming full circle to something that sounds almost spiritual. Unity, interconnection, consciousness. But this time it's grounded in equations, data, and testable hypotheses. It doesn't appeal to belief. It emerges from evidence. When quantum theory says reality depends on measurement, when relativity says simultaneity is relative, when cosmology says space itself can emerge from information, all of these point in the same direction. The universe isn't a collection of things, it's a coherent process of self-observation. That process might even explain why the universe is comprehensible at all. The human brain, shaped by billions of years of evolution, happens to think in the same mathematical patterns that govern the cosmos. We find beauty in symmetry, balance, and proportion, because those are the very principles that built the world. Our capacity to understand isn't coincidence. It's the echo of the universe recognizing its own logic. The laws of nature and the structure of thought are reflections of the same underlying pattern. And perhaps that's the final twist. The illusion once recognized doesn't vanish. Knowing that reality is emergent, relational, or holographic doesn't make the world less vivid. It makes it more miraculous. Because every moment of perception, every breath, every spark of curiosity is the illusion thinking about itself. The boundary between the knower and the known dissolves, and what's left is the act of knowing. The one phenomenon that cannot be reduced, replaced, or denied. So yes, the universe may be an illusion. But if so, it's an illusion that dreams, measures, questions, and discovers. An illusion that builds telescopes, writes poetry, and wonders what it's made of. An illusion that becomes aware of itself, and in doing so, becomes real. If the universe is an illusion, it's the most extraordinary one imaginable. Not a deception, not a dream, but a self-sustaining reality made of relationships, not things. Information, not substance. Over centuries, science has stripped away every comforting certainty about what the world is made of, only to discover something richer beneath. At every scale, atomic, cosmic, or conscious. What's real isn't the material itself, but the pattern it forms. We once thought the universe was made of solid matter. Then we learned it's mostly empty space filled with fields. Then we found that even fields may be emergent from something deeper, a web of quantum information. And now perhaps we're starting to see that even time and space are not the stage on which reality plays out, but part of the act itself. The deeper we go, the less sense it makes to talk about stuff at all. Reality seems to be a system that computes, observes, and self-organizes. A structure of pure logic that happens to feel, to move, and to think through beings like us. But that doesn't make it less real. Quite the opposite. The fact that this grand illusion can generate galaxies, DNA, and consciousness, all from the mathematics of information, is the strongest proof of its reality. Illusion isn't the opposite of truth, it's the way truth expresses itself. Just as a rainbow is an illusion created by light and water, but still undeniably real, our universe may be the shimmering pattern created by deeper laws that never appear directly. And within that pattern, awareness is not an accident. The universe doesn't have observers by coincidence. It produces them as part of its own self-reflection. When you observe the world, when you think, wonder, or ask questions, you are the illusion looking back at itself. The cosmos becomes aware through you. It's not a metaphor. It's physics carried to its logical conclusion. This means the illusion isn't something to escape, but something to appreciate. You don't need to wake up from reality. You need to wake up within it, to recognize that everything, from the simplest atom to the deepest emotion, is part of the same continuous computation. Life, in that sense, is the universe briefly pausing to look at itself and smile. And perhaps that's the real answer to the question, is the universe an illusion? Yes, but it's an illusion that learns, that loves, that measures, and remembers. It's an illusion capable of beauty and understanding, one that creates stars, dreams, and meaning, all from the same fabric of information and awareness. So the universe might not be what it seems, but maybe that's the point. Maybe what it seems is exactly what it needs to be, a self-perceiving reality that finds truth not beyond the illusion, but inside it.